with the presentation of a short documentary. We have made a short documentary on our university. I welcome you all. Before we formally start, we have 5 more minutes. So let us let us help on our university. A short documentary on our university. And for your kind information, I have posted the message that the program is also available live on YouTube. The program is also available in YouTube. I have posted the link in the chat box. I once again request you all to kindly put your phone, microphone, or the device in mute form for less noise. Kindly cooperate. If you have any questions to ask, put your question in the chat box, and the concerned chairperson will pass on the questions or your comments to the respective speakers. I would also request you, if you could kindly cooperate by also help us for better connectivity. You can put your mobile device in video on, no problem, but better connectivity would be possible if we put our devices on the video and the audio mode. If we put them off, that will help us for better connectivity. I once again humbly request you all to kindly cooperate with us. We will shortly start our program, but before that, let us start our program with the presentation of a short documentary on our university. I joined as the Vice Chancellor of this university in 2011. The infrastructure was very underdeveloped and it was in shambles. And it required great effort on our part to create an ideal infrastructure for like we were also working on the creation of the right infrastructure because most of the students in these universities we need to prepare our students for the competition they may be, and we have to respond to the needs of the hour because the jobs are scarce, and in order to have them a better placement in life, we try to uh, gradually make our courses more in tune with modern requirements. And our teachers, my esteemed colleagues at this university, they wanted to see their university as one of the best in the country. And we seriously, we are trying to put the name of Vidyasagar University in the national and international academy. And in this job, we are partly successful. We believe in performance. I personally I sincerely apologize for the technical problem. So that was a short documentary on our university. On behalf of the organizing committee and the Chemical Research Society of India, Kharagpur local chapter, I welcome you all to the one-day webinar which has been jointly organized by Department of Artistry, Chemistry and Chemical Research Society of India, Kharagpur chapter. I'm glad to inform you that we have received responses from more than 400 participants across the country, entire India, starting from far west to the far east and north, like Jammu and Kashmir, to our southern fringes, so Kerala, and more than participants from more than 200 academic institutions have responded. So we are overwhelmed by your kind response. Now, Honorable Vice-Chancellor Professor Ranjan Chakrabarti was supposed to chair the inaugural session, but due to some exigency, he expressed his inability to inaugurate the program. He personally informed me that it would be his personal loss. He would have agreed, he would have enjoyed all the lectures throughout the day, but he has simultaneously requested Professor Subrata Kumar, Dean Faculty of Science, to kindly chair the session. I, Professor Amyo Kumar Panda, a faculty member in the Department of Chemistry, welcome you all, and I request Professor Ajay Kumar Misra to deliver the welcome address. But before that, let me tell you that we have 4 speakers today: Professor Hon'ble Samanta, Professor Nilmoni Sarkar, Professor Anindya Dutta, and Professor Nikhil Guchhait. In the inaugural session, we are going to listen from Professor Ajay Kumar Misra, the convener, Professor Subrata Kumar De, the chairman, and Professor Swagata Dasgupta, the convener of the CRSI Kharagpur chapter, and a formal vote of thanks. It will immediately follow the technical session. So without much delay, may I request Professor Ajay Kumar Misra to kindly deliver your welcome address. Professor Misra, please.
Thank you, Professor Panda. Good morning. Honorable Dean, Faculty of Science, Professor Subrata Kumar De, Convener CRSI Kharagpur Chapter, Professor Swagata Dasgupta, Co-Convener CRSI Kharagpur Chapter, Professor Amyo Kumar Panda, Honorable Resource Persons of today's webinar, Professor Anunay Samanta, Professor Nilmoni Sarkar, Professor Anindya Dutta, Professor Nikhil Guchhait, my esteemed colleagues of the department, and dear participants across India and abroad in this webinar. Today's webinar is organized jointly by the Department of Chemistry, Vidyasagar University, and Chemical Research Society of India, Kharagpur local chapter. As a convener, it gives me immense pleasure to welcome you all in today's webinar on recent advances in fluorescence spectroscopy. As you know, fluorescence spectroscopic techniques, be it in the steady state or in time resolve, are widely used in various fields of science like chemistry, physics, biology, material science, etc. It is a very sensitive technique to get information on microenvironments and are used both in vivo and in vitro study. If we go back to the history of research in fluorescence spectroscopy from Indian perspective, it is mainly initiated from West Bengal, and to be more specific, from Calcutta University and Indian Association for the Cultivation of Science, Kolkata. It has the legacy starting from Professor Sadhan Basu, Professor Mihir Chaudhary, Professor Konkon Bhattacharya, and interestingly, all the 4 resource persons of today's webinar are from the same school and bear the same legacy. So it is going to be a rare opportunity to all of us to listen the recent advances in fluorescence spectroscopy from the speakers who are internationally acclaimed authority in fluorescence spectroscopy. Now I take this opportunity to say a few words about the Department of Chemistry, Vidyasagar University. Our department has a long tradition of excellency of both teaching and research in chemistry. Present intake of the department in postgraduate course is 70 and the faculty strength of the department is 8. There are nearly 40 research scholars who are pursuing their PhD research in the department in various projects funded by EGC, CSIR, DST, DBT, etc. Our department is recognized by both DST and EGC through DST FEAST at level 1 and EGC SAP program. First area of research of the department is the synthesis of novel materials based on plant resources, low-dimensional organic materials, ionic liquids, organometallic complexes, and other allied areas are surfactant chemistry, protein nucleic acid interaction study, nanomaterial, and computational chemistry. On an average, 60 to 70 research articles are published in each year from the department in various international journals with high impact factor. Faculty members are also involved in collaborative research work with national and international institutions. Department has a strong alumni who are placed in various IITs, NITs, university, colleges, schools, and industry. Performance of a student in various national level exams like NET, GATE are praiseworthy. Lastly, we are thankful to our university authority. We are thankful to our university authority with the leadership of our Honorable Vice-Chancellor to create a conducive environment for both teaching and research. So with these few words, I once again welcome you all in today's national webinar on recent advances in fluorescence spectroscopy. Thank you.
Thank you, Professor Ajay Kumar Misra, for your welcome address. Just I would like to tell you once again, the program is it is streaming live. Live streaming of the program is available on the YouTube. I have already shared it with in the chat box. So kindly do not hesitate to forward it to your fellow colleagues. I would like to inform you that we are also having some delegates from our neighboring countries like Bangladesh, Nepal, and Bhutan. So I also welcome you all. Now, may I request Professor Swagata Dasgupta, the convener of the Chemical Research Society of India, Kharagpur chapter, and a professor of chemistry. He is also the dean, to kindly deliver your address and also introduce the speakers and the activities of the CRSI. Professor Swagata Dasgupta, please.
Thank you, Amyo. Am I audible?
Yeah, you are audible.
Okay. A very warm welcome to all of you in the recent advances in fluorescence spectroscopy, a webinar that is being organized by Vidyasagar University. The co-convener of the CRSI local chapter of Kharagpur is Professor Amyo Panda, and I happen to be the convener of the CRSI local chapter Kharagpur. In the pandemic times that we now are in, it gives me immense pleasure that at least a webinar could be organized where even though we are so far away, we are close in a sense in we have an internet connection. It is sad that we cannot do this in person, which obviously gives a much more closer feeling, a much more bigger network. At first, I would like to give a warm welcome to our Professor Subrata, the Dean Faculty of Science. I understand that the Vice-Chancellor could not be present today. Professor Ajay Misra, who kindly agreed to be the convener of the webinar. The co-convener, Professor Amyo Panda of the local chapter. Distinguished speakers faculty colleagues, research scholars, students, and friends. The activities of CRSI have increased manyfold over the years. It was instituted in 1999, and CRSI is proud to have connections with leading chemical societies around the world. There are several meetings held over the year, and the local chapters have been asked to popularize chemistry in the region by various activities such as these. This is one such activity where the endeavor is a webinar on this specific topic. But besides that, each local chapter is supposed to bring about college teachers' education, fun things for the students, and any sort of activity suggestions would be most welcome from any of you. The CRSI has over 2,800 life members, and it plans several events over the year. Today, we are very happy to have in this webinar Recent Advances in Fluorescence Spectroscopy 4 distinguished researchers in the specific field, as was mentioned by Professor Ajay Misra. One thing I would like to say about each of them, or all of them rather, is they work in fluorescence spectroscopy, work with excited states. But each of them are very down-to-earth, grounded people themselves. I know them personally. They're in the ground state. And we are delighted to have them with us today. I thank the efforts of Vidyasagar University, their computer center, particularly the co-convener, Omio, who has put in a tremendous effort to get this together, for the untiring efforts of the other faculty members, and of course, Professor Ajay Misra, the convener of the webinar. I hope we have a wonderful day today, and I welcome you once again on my own behalf. Thank you.
Thank you, Professor Dasgupta, for your valued speech. And I hope I also do agree with you that although the speakers will be discussing on the excited state phenomena, but yes, they are really very down to earth. That's why when I just sent an email to all of them, they immediately responded. And everybody knows that how busy they are in their professional life. So, yes, I do agree with you. Now, may I request Professor Subrata Kumar De, Dean Faculty of Science and the Chairperson of today's program, to kindly deliver your presidential address. Professor Subrata Kumar De, please.
So, thank you, Professor Panda. Good morning. And under the able leadership of Professor Ranjan Chakrabarti, the Honorable Vice-Chancellor of Vidyasagar University, the Department of Chemistry and the Chemical Research Society of India, Kharagpur Chapter, West Bengal, is jointly organized a webinar in this pandemic moment. In this occasion, I just mentioned the name of Professor Ajay Misra, the convener, on behalf of our university of this national webinar. Professor Swagata Dasgupta, she is also the convener of CRSI, Kharagpur chapter, and the convener, also co-convener, Professor Panda, he is also the faculty member of Vidyasagar University. The head of the department, Professor Sudipto Doloi, and the resource person, eminent resource person of this webinar, just recent advances in fluorescence spectroscopy, a respected professor, Professor Anunay Samanta from University of Hyderabad, Professor Nilmoni Sarkar, IIT Kharagpur, Professor Anindya, IIT Bombay, Professor Nilkamal Guchhait, Nikhil Guchhait, extremely sorry, Calcutta University, the senior faculty members of our university, and the participants from national and international forum, research scholars, students, officials, and if any press and media personnel is present, ladies and gentlemen. Simply I say that it is a special field, that is a fluorescence spectroscopy, and I am not in the field, but I say I am a microscopist, I work on microscope, and from my experience, when I observed any type of cells under microscope, the microscope type are different, in different mode to different action, like light microscope, scanning electron microscope, transmission electron microscope, high voltage electron microscope, atomic force microscope, scanning tunneling electron microscope, different categories of microscope. From my experience, that each and every microscope is give some information related to cell. So chemistry, when I lead to chemistry, and this chemistry is the central subject of science from my opinion and from my expectation. It is the leading subject. And this leading subject deals with several fields. And fluorescence spectroscopy is a special field of or specimens of different reactions or different position. And these elements are used in different fields in science, especially in physics, chemistry, astronomy, tissue analysis, medicine, medical imaging, environmental monitoring, mining, and etc., etc. And when we work in this field, the scientists are raise few questions. The specialist or the resource person raise some question in their own field, and they solve it with the help of some special instrument. And such type of instrument is a fluorescence spectroscopy. And this type of webinar in this pandemic situation, I think it gives some fresh oxygen to our students, research scholars. They nurtured their hypothalamus or their mind. And when they nurtured their mind, they acclimatize their situation, their present situation. And they can able to habituate or adapt their recent examination system or recent working system. And this unlock 4 stage. So it gives some immense pleasure to the students, to the researchers, and the learned audience also. I think this exposure under the able leadership of our Vice-Chancellor and the local chapter of recent Chemical Research Society of India, Kharagpur chapter, they just convey this type of technique. I think the feedback will give enough mileage to the students, to the research scholars. With these few words, I say virtually inaugurate or declared this national webinar is open. And when this seminar is open, then each and everyone can enjoy the 4 or 5 hours webinar in this time. With this few words, I congratulate again to just organize such type of a brilliant webinar in our university with the help of a CRSI, and I put my pranam to all resource persons and their able guidance. Any shortcoming, please excuse us. With this few words, again, I congratulate all participants who welcome this national webinar. Thank you. Thank you all.
Thank you, sir, Professor Subrata Kumar, the Dean Faculty of Science, for your inspiring lecture. I'm sure your speech will instill among all the sections, be it the participant, be it the organizer, and the speakers as well. And I'm also glad to inform you that our speakers are already there on the online. So I welcome the speakers to our webinar. And now I request our senior most faculty member in the chemistry department of chemistry to kindly deliver the vote of thanks. Professor Gopal Bagh, please. The vote of thanks will be delivered by Professor Gopal Bagh. Professor Bagh.
Thank you, Professor Panda, and good morning to you all. The Dean Faculty of Science, Professor Subrata Kumar, our today's speakers, Professor Anunay Samanta, Professor Nilmoni Sarkar, Professor Anindya Dutta, and Professor Nikhil Guchhait, and then Professor Swagata Dasgupta, Convener of CRSI IIT Kharagpur Local Chapter, and also co-convener Professor Amyo Kumar Panda, and respected dignitaries, ladies and gentlemen. It's my proud privilege to have the honor to propose a vote of thanks on this occasion. The first Chemical Research Society of India one-day national webinar jointly organized by the Department of Chemistry of both Vidyasagar University and IIT Kharagpur. I, on behalf of Vidyasagar University and the entire fraternity gathered here today, including the media persons and on my own behalf, extend a very hearty vote of thanks to our honorable speakers for kindly responding to our invitation in spite of the schedule. I also thank Professor Subrata Kumar, Dean Faculty of Science, for his moral support and encouragement, and also kindly inaugurating this session. And also we are thankful to Professor Swagata Dasgupta, convener of CRSI IIT Kharagpur Local Chapter, and co-convener Professor Amyo Kumar Panda, who took active interest jointly to organize such a program. We are also thankful to all the faculty members and university officials, supporting staff members, students, and research scholars, media persons to be present here to make this event a success. Last but not the least, we thank Chemical Research Society of India for extending their cooperation and support. Thank you very much.
Thank you, Janardana.
Thank you, Professor Bagh, for your formal vote of thanks. I once again request everyone other than the speaker, please mute your phone device so for the smooth conduction of the program. Kindly cooperate. As I mentioned, the program is being streamed in two platforms. One is the Google Meet, another is in the YouTube. More than 100 participants are there. They're enjoying the program in the YouTube channel. So with this, let me conclude the inaugural session and we'll immediately move to the first technical session. And the first technical session will be chaired by Professor Ajay Kumar Misra, and the speakers are none but Professor Anunay Samanta and Professor Nilmoni Sarkar. So may I now request Professor Ajay Misra to take over. Over to you, Professor Misra. And just let me once again request you all to kindly put your device in mute form. Please do not go for presenting your material when Professor Samanta or the speaker will be presenting. Now the screen will be shared by the speaker immediately after the introduction by the chairman. Professor Misra, please.
Thank you, Professor Panda. So now we are going to start the first technical session of today's webinar. In this session, we will listen from two eminent speakers, Professor Onunay Samanta from University of Hyderabad and Professor Nilmoni Sarkar from IIT Kharagpur. So I will request the speaker to restrict their lecture within 40 minutes and 5 minutes will be the question and answer session. Participants may put their question in the text box also, the chat box. Now, our first speaker is Professor Onunay Samanta. Actually, Professor Onunay Samanta is a well-known personality both nationally and internationally in the field of fluorescence spectroscopy. After completing his PhD research from ISS under the legendary teacher and spectroscopist of our country, late Professor B. Chaudhary, in the year 1987, Professor Samanta moved to Radiation Laboratory, University of Notre Dame, USA, for postdoctoral research during 87 to 89. He then joined the School of Chemistry, University of Hyderabad as lecturer in the year 1990, and presently he is the Dean School of Chemistry, University of Hyderabad. Due to his excellent research contribution in the field of spectroscopy and particularly in fluorescence spectroscopy, he has been awarded and recognized by a number of scientific bodies of both India and abroad. To name a few, he is the elected fellow of Indian Academy of Science, National Academy of Science, Indian National Science Academy. He has also been awarded Raman Fellowship by DST. He is a J.C. Bose National Fellow. He has also been awarded with Chemical Research Society of India by Bronze Medal, and he also received the Silver Medal also. And Professor Sadhan Basu Memorial Award. He also received the R.P. Mitra Memorial Lecture from Delhi University, and he is the elected fellow West Bengal Academy of Science and Technology, and he is also the editor in the chemistry section of proceedings of INSA, and he also been awarded with A.V. Ramarao Foundation Lecture in Chemistry, and Ramon Mijusima Lecture Award by JSPS DST in 2014, and also he has been awarded APA Award by ASEAN and Oceanian Photochemistry Association Taipei, Taiwan in 2018. His present research interest involves the spectroscopy and dynamics of short-lived species formed in photoexcitation of molecular system and materials using time-dissolved fluorescence and ultra-fast palm probe techniques. His group also involved in research using time-dissolved confocal fluorescence spectroscopy, microscopy, and fluorescence lifetime imaging and single molecular fluorescence techniques such as fluorescence correlation spectroscopy. Currently, his group engaged in the study of charge carrier dynamics and fluorescence blinking in a variety of photoexcited perovskite nanocrystal of different morphologies, photoexcited processes in semiconductor quantum dots, solute and solvent dynamics, and understanding the nature of ionic liquids and deep eutectic solvents. So with these few words, I invite Professor Samanta to deliver his lecture.
So over to Professor Samanta. The screen is yours.
Okay, let me share.
And once again, I request everyone to mute your device.
I'm having some technical problem. Let me see. Why this? Are you working something yesterday? Why presentation is not working? Presentation is not working.
No, it is not working. We cannot see your presentation.
Do you need permission for presentation from the host?
I don't know. It is not asking that. present now button is not active. It says present. Just wait.
Biplab Babu. Anindo Datta is present. Actually, Anindo.
Yeah, I am able to present.
And it says you must grant permission
Oh.
in order to screen share. You must grant permission. Who is going to grant me permission to screen share?
You yourself. You yourself.
You just say share and it should come.
But if he's getting that message, then
maybe if you leave the meeting and re-enter, it might work.
That is better.
Yeah, kindly bear with us. Kindly bear with us.
Meanwhile, Niluda, you might want to give it a try to see if yours works somehow.
Professor Samanta, you are muted. We cannot hear you.
I did that, but then let me go to settings window. You must grant permission. Again, I am getting same thing. Yes. Just a minute.
When you press the present now, it is not working.
Just a minute. No, it says that you need permission. It says, I'm getting a message. A window, let me see. You must grant permissions in order to screen share.
Oh. Omyo, can you ask Biplab? He can.
No, you must grant permission means it is Professor Samanta who should allow.
Now, how do I allow? That's it. How do I allow? I went to settings. I am there, very much there. Now, share.
Biplab Babu, are you there? Biplab Babu or Sunil Babu, are you there? Biplab Babu or Sunil Babu? Mr. Biplab Chakrabarti or Mr.
Professor Samanta, when you go to present now, what do you
Yes.
does it tell you to share the screen? Then you share the screen or share the entire screen. These are the two options you will get. Then you have to click on one of them. Click on any one of them.
I click both. I tried both earlier. Let's say, for example, I tried entire screen. I give. It says cannot share your screen. You must grant permissions in order to screen share. Now, where
And the
is the
share
permission?
option does not highlight. It should come up in blue.
Let me see.
Nilmoni, you want to try yours to see if it's coming?
No, where it is? It is the Zoom thing or it is the other network?
No.
It is not
Actually, when you say present now, you should get another window that pops up, and then there will be separate options.
Yeah, I know.
I'm sure you've done it before.
Many meetings.
I'm sure you've done it before.
I've done many meetings.
Yeah.
That is why I am surprised.
Yeah, it's quite surprising because this is very common nowadays.
It will be entire screen.
Yes, if you click entire screen, then we will see your entire screen, and then you can choose your presentation.
Oh, I see present now. I see my entire screen. Then it says you must grant permission, but then it is not giving any options. That's the problem.
That's funny. Because Professor Anindya could share.
I don't know.
Then Omyo has been sharing the presentation. And we had another few presentations pop up while we were doing it.
Nilmoni, would you give a try?
Sir, don't use entire screen. Sir, a window, then you can see, sir.
Okay,
Present
I have
now
to give
a window.
a window give.
Yes, sir.
That also is the same mistake.
It is showing you must grant permission in order to screen share.
Oh,
Same
Nilmoni has the same problem.
I think you have to give permission. I think I don't know. So because
But how come Anindya has permission?
I don't know. Anindo is big shot. You know.
Anindya,
I don't know.
this?
Anindo is presenting that is coming, but then
No, they like me more.
You are present now. You must grant permission. Now, who is granting permission? Normally, control is their side, no? Your side.
Exactly.
You
But
have
how
to
did
allow.
Anindya, what special thing have you done to get in?
Present করতে but you must grant.
Maybe you could call somebody and find out.
Yeah, I already called, and he said no, there no permission from the host side is required. Just you need to have you activated the window, Professor Samanta?
What do you mean? Activated the window means
that your PowerPoint is open, right?
Yes, my PowerPoint is open.
Yeah, but no permission is required from our side, from the host side.
But I also cannot do this.
But how did you enter the Google Meet? Did you enter from the email sent?
Yeah.
Maybe that might be an issue. If you enter through from the email sent, that probably automatically grants you permission. Maybe, I'm not very sure.
Do that again?
I'm not sure. That's the only option I can say.
Let me do that again. Let me.
Brother Samanta, how big is your file? If you can send it to us, then we can.
He has left the meeting. He's joining through the Google Meet link received an email. Maybe that probably grants them automatic permission. I'm not sure. Let them try.
No, it is showing the same thing. You cannot share your screen. I don't know.
No, but you use the link that I sent from the meeting schedule. You just go to your Google Calendar. Because if the others, they cannot present. Only the speakers or the host, they can present. And that we did in that way.
Niluda, can you do it?
No, I cannot do it.
Anindya?
Yeah.
Anindya did it.
Only Anindya can do it, right?
Answer one question. Did you send us two different links, one for the speaker and one for the audience?
No. When I sent an email link using the Google Meet, that was automatically saved or stored in your Google Calendar or Meet drive folder. And I think you opened using that, not through the email, right?
No, I opened the email and
Professor Samanta, can you unmute?
I have no problem in joining. Continuously, I am getting the same thing.
Now, may I request you one thing? How big is your file? Can you send it by email so that I can display? Bhiguram Das is presenting. Everyone is presenting. Bhiguram, please come.
Everyone else can present except the speaker.
Now we can see two screens. Professor Samanta, we see two screens.
I'm just getting rid of.
Nikhil, could you present yours?
I have not tried. I can try it.
Yeah.
This is real problem. I've never faced this problem. Never. Every day we are having a meeting with all sorts of.
Yeah.
Exactly. This is a very common thing nowadays.
Sir, before joining present now, enter into present now option.
There is another option. Before joining, you can just present now.
Yes, sir. It is working.
Habiba, stop presenting. Habiba, you are not supposed to. Everyone else can present.
I will try a different browser, okay? Just a minute. Just a
Sure.
That's the only thing I will try now.
Select window or screen, then allow, no? It is not activated. Why?
Mine is not working.
Huh?
My part is only working.
What?
Nilmoni could present. Sorry, Nikhil could present.
Yeah, I think so.
Just a minute. I'm just trying a different browser.
I can try this one.
Let me see now. Yes, now I can share. Okay. Okay.
Perfect. Great. Okay. Great. Okay.
It's just a browser problem, not a. Okay. Can I start now?
Sure.
I think I got.
Yes.
Okay. I think let me begin by thanking the organizers, the CRSI Kharagpur chapter, and both and the Vidyasagar University, and the two persons behind this organization. Let me not name. The title of my talk is single molecule fluorescence and its fluctuations. That's the title I gave, because it was the webinar title is Recent Advances in Fluorescence Spectroscopy. So I thought, this is a fairly new technique. Not many students are aware of this technique. And let me discuss some, basics and some exciting features about single molecule fluorescence. That's the whole idea. I don't think that I am going to talk much research, my research in this thing, because much of it these days, of course, there is some single molecule fluorescence spectroscopy, but there is also a lot of pump probe spectroscopy. So that is the main problem. Well, this institute, our university has recently been awarded this Institute of Eminence tag, and it's a good thing. Let's hope that our university, we can raise it to a different level. And this is one of the monuments, basically natural rock formation from our campus. Our campus is beautiful. It's a small university. It was founded in 1974. It has 5,100 plus students, 450 faculty, and we have a very large area, and much of it is not used. Okay, and these are some of the shots from this beautiful campus. Single molecule spectroscopy. Now the question would come, why single molecule study? That's the very first thing. The reason is this. Okay, for example, let's say I have two species, and as you can see, it has one closed form, and it has the molecule is actually like this. Two terminals are Q and F, and it can exist in open conformation, which is the fluorescent, and the other closed form is non-fluorescent. And hence, but if you record the fluorescence spectrum of this, species in which two species are there, then you will get basically that black line, which will give you the ensemble spectrum. You will not have any idea of the individual spectrum of the two forms. So, that is the main advantage, that actually open form has this green from that, and the do the single molecule spectroscopy. So that's the single molecule spectra. If you can recall, then you can basically record for each one and get this information. There is no other way you can get this, because otherwise things get averaged out and you end up in a situation like this black spectrum. Now detection. Now there are problems. You can see that if you want to detect the emission from a single molecule above the background level, it's a real problem, because impurities will be there, emission from optical components will be there, there will be dark counts. Now these things will be there, but even if those things are there, marker. That marker is basically the Raman spectrum of water. Now, even if you don't have anything, if you just take water, you have this signal. So now, how do you record this fluorescence of your dye? Let's say rhodamine 6G, which has this green fluorescence. Now that is difficult, because this one is basically a solution of 10 to the power minus 3 molar solution and 3 ml solution you have taken. But if you go to one molecule, you will not be able to see, but you will get Raman spectrum like this. So that's the problem. It's a very, very difficult way, to detect basically the single molecule fluorescence. And you see how to get rid of. Let's say, for example, I have no problems with our impurities and other noise. I have only problem with this, shown in this particular manner. If the volume is 1 ml, it can be shown that the Raman scattering intensity will be 10 to the power 10, some number. When its fluorescence intensity is 1, the Raman scattering intensity is this much. Okay, you can see this. Now, if you reduce the volume to 1 femtoliter, 1 femtoliter means 10 to the power minus 15 liter. It's a very, very small volume. Then you can see your fluorescence intensity is 1.0, and the Raman scattering intensity is 100-fold less. So there is a way. Then you can detect basically your fluorescence, and Raman scattering will not be a problem. So basically, if you want to do single molecule fluorescence study, then you have to concentrate to a very small volume, and typically 1 femtoliter or 10 to the power minus 15 liter volume. Well, when you do the experiments in the lab, conventional spectrophotometer, we take 3 ml solution like this, and how many molecules are there in that? Roughly 3 ml of 10 to the power minus 4 molar solution, let's say 10 to the power minus 4 molar. So I think, yes. So basically 3 into 10 to the power minus 4, that is in 1 liter. So 3 ml means, basically it's a 3 liter. And then 10 to the power minus 4 molar, multiply by Avogadro number. You are looking at the signal of, 1.8 into 10 to the power 17 number of molecules, even though your solution is very, very dilute. With this kind of dilute solutions, you cannot record, NMR spectrum or IR spectrum. Okay, we are using very dilute solution, 3 ml of it, but even then we are still in this many molecules. And here we are talking about, single molecule fluorescence, detecting fluorescence from a single molecule. Now, how to look at such molecule? Obviously, our naked eye cannot do. Our naked eye, no matter how tightly you focus, you will basically see some minimum volume. Okay, so what you have to do, it has to be seen through a microscope. I would say it's a confocal microscope. It has to be done through this instrument. So microscope will basically ensure that we are looking at a single spot. This spot, for example, it's a focal point. You can see that. Let me tell you something about this. Your excitation laser beams, come these blue lines, parallel lines, and then there is a lens, objective lens, and it tightly focuses. I'm talking about this small volume. And as you know, in addition to this small volume, it will expose a larger volume. So what you have to do, you are exposing still, although focusing is one point, but then there are other areas which are also focused. And then problem is that, you will have basically a large area. Now, if you want to collect the data only from this point, then you have to have another technique. When they go back, you can look at this green line, and then you can see green lines are going everywhere. Now, what you can do, you can use a pinhole, very small pinhole, typically a micrometer size pinhole. Then this spot size will be equal to this focal spot. So with this kind of arrangement, you have to block everything, apertures and etc. So using this pinhole, you can ensure that, whatever you are collecting here is basically coming from the focal spot. What's the size of this spot? Now, one can look at simple physics. If the numerical aperture of the lens is 0.5, actually we use much, higher numerical aperture. So the size is even smaller. Even if I take it 0.5 and you use 400 nanometer, basically the focal size is given by lambda by 2 numerical aperture, and that will give you typically 1 femtoliter. You can make it even smaller by increasing the numerical aperture. That's the way to look at single molecule. So single molecule spectroscopy, if you have to see, you have to use a confocal fluorescence microscopy setup, not fluorescence microscopy just like that. Okay. Now, for example, there are different ways of looking at the samples. Say, for example, you can take a very dilute solution and you can spread them, and then you can look at them. And if they are single molecule, then they will look like this. You can see nicely there. These are very, very dilute solutions. 10 to the power minus 12 molar solutions are there. It is sprayed on basically some cover slip. It is dried. And then this image is constructed by a confocal microscope. Okay, not by, you can use, I will show you that some wide field microscope also you can show. The problem is that when you look at this, there are some issues like photo bleaching you can do. Molecules do not tolerate light. We don't feel it. But when we are looking at only one molecule, we can see that light is there and immediately it is gone. And then when you immobilize them on a surface, there are other issues. Say, for example, if you wanted to study, conformational motions like this, you cannot study in these immobilized conditions. So there is another way you can study mobilized samples as well as immobilized samples. Now, let me show you one diagram. This is not my diagram. It is taken from some website. You can see this is the slit. In slit, I can see that there are some particles here. There are some particles. You can see what they're doing. They're not stable. That's the point that I want you to look at. That's what I call you fluorescence blinking. What I am doing, I am looking at single molecules, and what I find, these molecules are blinking. They are fluctuating. In addition to this fluctuation, you can see also another thing. You can see there are less number of molecules, and as the time progresses, more and more molecules will come. That is what is called photoactivation. That means each molecule is there, that itself is blinking. There is no period here, irregular blinking. And also in addition to this, now we can see this part is really glowing. So there are two processes going on. Let's not bother about the photoactivation thing. That is another phenomenon which you can study through the single molecule fluorescence. But what I want you to look at is this, blinking, these fluctuations. That's what I want you to know. Let's go to fluorescence blinking. Now the question is, you wanted to see single molecule. Now when you see the single molecule, able to see fluorescence single molecule, then you see that they are stable. Why they blink? Why a molecule is stable? Why a nanocrystal? These days, the fluorescent materials are more like particles, like quantum, chalcogenide quantum dots. They are nanocrystals of, like perovskites, what you study. Why do they blink? They blink because when you shine light, if this particle undergoing this off transition between ground state and on state, then you will see it glow. But when this particle goes to the off state, which can be a triplet state for a molecule, and it can be a trap state, non-fluorescent trap state for a particle. When it goes there, like in this case, you are exciting, the particle is going to the trap state and coming like this. So this is basically the dark phase. And if it is undergoing this cycle, then it is on. So this is what is fluorescence blinking. So a molecule indicates that it has trap states, or it has non-fluorescent states. That's what we learn. So if we study this blinking dynamics, then we are able to say something about these kind of processes, that such a state is there, and quantitative analysis of the data will allow you to get kinetic information about these processes, also the nature of these states. Now again, this blinking, blinking, this is same thing I said that, blinking, if you have to see, you cannot see it, with an ensemble system. It's because it is difficult to see a single molecule. That's difficult, fine. But then when you have more molecules, then it is even more difficult to see the blinking because there are so many other particles which are not blinking. So they will mask this blinking. So that is the beauty. So it has to be a single molecule spectroscopy. Okay. Now, the picture that I showed, the video that I showed was very interesting. That shows really blinking. And that is, you are using a wide field microscope and then you can see simultaneously a large number of particles. On the other hand, if we are using confocal microscopy, and then what you see here, and we are looking at only one particle, what do we are seeing? This is the fluorescence level. You can see this level. This level, you can see that it has a fluorescence, and then sometimes, it comes down. These are basically dark state. And you can see these periods and etc., they are very, different. In this case, this fluctuation is much more, the occurrence of the dark state is much more. You can see that. I have also basically a statistical diagram. You can see that occurrence of the on state is much more here. Here, occurrence of off state is much more. So we analyze in these kind of things. These are from immobilized samples. Now, if we are not happy with this, immobilized sample, there are reasons for you to not to be happy. Because if you are not interested in solid state, if you are interested in solution spectroscopy, and if you want to see molecular conformational changes and other things which occur in solution but not in solid state, then you have to go for another spectroscopy that is called fluorescence correlation spectroscopy. This also is a single molecule spectroscopy, and it was basically theoretically it was proposed quite early in 1972, but it could not be realized or practiced. It cannot be applied really. It's because of there are many issues. You can see that you have to have a confocal this optical geometry that thing should come. You have to improve the signal to noise ratio. You have to have a very stable solid state lasers whose which should not fluctuate. We are looking at the fluctuations of fluorescence intensity, but not because of voltage fluctuation or because of laser intensity fluctuation. the detectors is another thing. You have to have detectors, which can pick up the fluorescence from only one molecule. These things took time, and that is why it has taken a long time. It has been made practice only in 1990s. Now, I already mentioned that this femtoliter volume we choose normally. This one I have already said. Now, how dilute is the solution? If I want to really see a small, one or two molecules, then I have a small calculation. If I use 10 to the power minus 10 to the power minus 9 molar solution, then I am dealing with basically these many molecules. I calculate the number of molecules for a liter, and then for 10 to the power minus 15 liter, I calculate its volume is 0.6. So that's a very small number. This is an average number. So if I am working with a configuration, that means I'm looking at 1 femtoliter volume and a dilute solution I am using, nanomolar solution, then I am essentially looking on the average, 0.6 number of molecules. So I am working in the single molecule condition. So what is done here? You can see that. Let's bother about this is the volume I am observing, and I'm saying this volume is 1 femtoliter, and let's say particle is there. I will tell you how the particles are placed. The particle, one drop of solution is basically placed between two cover slip, one drop. Okay, so particles diffuse, and I am showing basically a diffusion of a particle. So if I see this phenomenon for a long period of time, I get this kind of noisy picture. This kind of very noisy picture. They look like noise, but this is the fluctuation spectroscopy. Okay, this is not really noise. This fluctuation. Why is this fluctuation? This fluctuation is because of molecule is diffusing. There are sometimes, when the low intensity is there, that means there is no molecule. Sometimes when there is one molecule, you have moderate intensity. When there are two molecules, then two more intensity like this. So it's basically fluctuation it is not because of any other thing. It is because of the diffusion of molecules and change in the number of molecules. It can be 1, it can be 0, it can be 2, 3, like this. So you have a data like this. Now, in this technique, a mathematical procedure is there. From this, you can calculate a correlation function, autocorrelation function, which is defined by, from these figures, basically, LF T plus tau and delta T, how this signal is correlated with another signal at some time. And if you see the time dependence, then basically your analyzed data will look like a curve like this. And you basically get all the information from this curve. Okay. Now, the point is that I'm showing here only the diffusion, but this this time, for example, this change of the curve need not be only for diffusion. It can be for many other factors. But from this diagram, you can extract the diffusion constants, you can extract concentration, you can extract the hydrodynamic radius of the system, how bright the molecule is, etc. And these are some of the factors. Sorry. These are some of the factors that can contribute to fluctuation. This is the most common. I am dealing with a solution, so diffusion is there first. But then in addition to diffusion, there can be many other things. When the molecule enters, during its passage through this observation volume, its fluorescence intensity can change because it binds to something, it can aggregate something, it can change its location from some hydrophobic to hydrophilic region. If we are dealing with a micellar solution, there can be a basically conformational change. I can have cis-trans isomerization, and the two forms, if they are different in fluorescence, that also can give fluctuations. So not just the diffusion, there can be many other factors which can contribute to the fluctuation of the fluorescence. And if you know the reason of fluctuation, then you can extract information about the kinetics of the process. But one thing you must sure that these are unwanted background fluorescence, scattering, impurities, etc. These are not wanted. These are the unwanted information, not appreciated. How it is done, this is how it is done. This is the, geometry, schematic diagram of the geometry. We use some laser source, and then laser source is directed through a dichroic mirror. And this is where the cover slip is there. One drop of solution is there. You can see it focuses on this one particular spot. And then what happens is that let's say the molecule emits green fluorescence. The green fluorescence comes through this. And I mentioned to you the importance of the pinhole. The smaller the pinhole, the better the thing is. That means the smaller the region that you are probing. Okay, then you can basically, this is a detector, it has a name, avalanche, photodiode detector, and you can get correlation curve. And this analysis of the curve will give you some time, diffusion time. The problem with this is that, you can see that, if you are using one detector, then, there are issues like this. If you see suddenly this fluctuation. Now, this is real, this black line is real, but then only if this fluctuation is because of some other factors. If you are using two detectors instead of one, then basically if there is a voltage fluctuation or laser intensity fluctuation, and for which this sudden spike came, then basically this can be taken read off. Then if you use both detectors, then they will cancel each other, and then you will get this noise-free detection. So actually what is done, it's the same thing. This is what we use in our apparatus. As you can see that we have basically same thing. Only here I am splitting it into two and then taking basically two avalanche photodiodes, and basically this is a cross correlation function. And these are the different components. This is basically the optical chamber. We have many such laser systems, and this is the confocal microscope system, and this is where the sample is. And this is basically the other part of this chamber where the dual APD, etc. there. Okay. Now, I decided, as I mentioned, that if nothing is happening like rhodamine 123, you get a curve like this, that will give you diffusion time. You know the volume. You can basically calculate diffusion coefficients. Okay. Now, if get a curve like this, you tried 3 different samples, or you tried the same molecule in 3 different medium, viscous medium. You can see this diffusion is fast and this diffusion is slow. So the nature of the curve will change. That will give you the information. Okay. If the size changes, molecular size changes, for example, same medium, but you take a polymer with the different molecular weights, they will give 3 different curves like this. Heavy molecular weight polymer will diffuse slowly, and you can basically extract using some simple formulas, molecular weight and etc. Apart from the diffusion coefficient, that's it. There can be 2-component diffusions. If there is a heterogeneity, you can see that it's not just you feed the data, it's a 2-component diffusion. Well, there can be fluctuations because of other factors, like there can be many other things, as I mentioned, intersystem crossing. If the molecule goes to intersystem crossing, that will also give rise to fluctuations, conformational change, photophysical changes. Now, that kind of things, for example, is illustrated here. For example, I'm studying this equilibrium. You can see there are 2 forms of this phenolic derivative. One is anionic form is bright, and the other neutral form is dark. So when molecule goes through this observation volume, it is diffusing. So there will be long component, which is diffusion, which is always constant. Because these 2 species, they will diffuse at the same rate. But what happens is that this process takes place, and that also lead to fluctuation, and so it will affect this correlation curve in the early time region. So by analysis, we can find out information about this particular process in addition to the diffusion process. Okay. Now, say because I think at the end, I have basically technique-wise, I mentioned, what I wanted to say. Now, there is no point in learning technique, unless you know some applications. So we are recently studying, semiconductor nanocrystals. So semiconductors are basically, that these are bulk semiconductors. They have a band structure like conduction band, valence band. But if you reduce the size, band structure disappears, and they form basically discrete energy levels like molecules. You can basically confine the semiconductor in 1 dimension, in 2 dimension, in 3 dimension, and the resulting species will be 0-dimensional, 1-dimensional, and 2-dimensional. This is the plate, this is the rod or wire, and this is basically dot. Okay, so dot is basically 3 dimensions from chloride to bromide to iodide. So you have two parameters you can vary, and you can have a wide tunability, high fluorescence. So these particles, nanocrystals, they are useful for photovoltaics. I just tell you this why they are. And then they are also used for optoelectronics, like light emitting diodes, lasers, photodetectors, etc. You know, these are, all of you know the dye sensitized solar cell, the principle. But dye is used. But dye absorbs only a very small region of the solar spectrum, visible portion. So when you can see the solar spectrum, only 43% of the solar spectrum is visible. So if you take a dye which absorbs only in the visible, you are losing real efficiency. So you need materials which will absorb much more intensely and much more broad absorption they should have. If you have, use basically these nanocrystals as just sensitizers, just absorbing species. They will take the solar light, they will absorb the solar light and then generate electron and hole, and that will generate basically photoelectric current. And so that's the beauty of this thing. And you can see that 2009, the first paper came. That was not with nanocrystals. This came with basically the bulk perovskite material. So you can see that efficiency was not very much, 5% or something like this. But then say these are three charts. Solar cell, dye sensitized solar cell efficiency has not increased over a period of years from 1990 to 2020. You can see this lead sulfide selenide based quantum dots, it increased efficiency over a period of years. But for perovskite, you can see it's a very steep curve, and the efficiency is 25+%. So they are very, very good absorber, and they also have many other properties, and that's why they are very interesting. Let me now talk about our interest is basically, we are not going to develop solar cells. We are interested in, we generate electron and hole, and then we want to find out, whether it is a hot electron, hot hole, how long they stay, how they decombine. Because the whole idea is, if you want to improve the perovskite-based solar cell, efficiency, then what you want to need, you need to remove the electron and hole quickly. Okay, so you need to know these deactivation pathways, and that is what we are interested in. We are also interested in photoluminescence because we want, they are important from, as I mentioned, many such light emitting applications like this. And so our studies basically are based mainly on pump probe, but let me not go into it. I think I am taking time. Let me not go into this. This is what our studies. You see that these particles, these are the our particles. Not any other particle. These are CS, PB, Br3, perovskite nanocrystals, picomolar solution, drop casted, and we have great difficulty, we have constructed this kind of image. Now, what we do, we basically analyze, say, 60 nanocrystals. Each and every nanocrystal we look at individually, look at their blinking pattern. You can see the blinking pattern. We see that 30% showing this kind of pattern, and 70% of the nanocrystals show this kind of pattern, which is not really blinking but flickering, because you can see that in blinking, on-off states are very well defined. Off means it is coming to the zero level. In this case, some particles are not coming to the zero level. It is basically never coming to the zero level. It is in the midway. It's like it is never zero. So why these pictures? That is the beauty. We are looking at single particles and looking at their blinking behavior, and we analyze. Let me not go into this complex analysis, but then the whole idea, this tells something, this tells me something else. So that is what we do. Then when we treat with thiol, then we see something like this. So this is the kind of applications that we do, single molecule study that we do. And then, I think I will just skip. There are many other things. We also do some fluorescence correlation spectroscopy thing. Let me, many studies, we have done, this will be too difficult for you to go through. And if the time was there, then I would have discussed, you could have got the essence. But for example, this kind of FCA study, for example, this is a solution state study. You can see we get correlation curve like this. What we are doing, we are basically varying the intensity of the result light, and we are seeing some change in this kind of change. When the intensity is high, intensity is low, then I see that, curve is here. And when the intensity is high, the curve is here. Now, these things are proportional to the number of molecules. And if I normalize this data, then they look like this. You can see this look like this. And what you find here is that, look at this, when I'm varying intensity, something is not changing. You can see that this is a diffusion. Diffusion is not changing. But there is another component here, and that another component is basically this blinking. In this study, it is not very visual. Fluorescence correlation spectroscopy study, the blinking will not be visual like in the frozen, samples. Okay, we get samples like this. I think this is the type of experiments, that we have been doing, with reference to the single molecule fluorescence. I think I will.
Single molecule fluorescence spectroscopy.
Well, there are a lot of limitations. There are a lot of limitations. If the molecule does not have high quantum yield, we may not be able to look at it. That's the main limitation. And the the instrumentation is quite expensive. Every component is very, very expensive. So that's.
And in the diagram, there is one trap state. Is there?
Yeah.
You have assigned that trap state as the triplet state.
Well, in the case of molecule, we know that when I am talking about nanoparticles, I am not saying that is a triplet state. Okay, I am saying that is a trap state. I don't know actual nature. Say, for example, the trap state can be many things. It's a defect state basically. That need not be a trap state where your carrier or hole, electron and hole are the carrier where they can be trapped. Okay.
Yes.
So I mean that's the state. I know it doesn't really matter the multiplicity of that state. It's not a triplet state. If it is a molecule, the most common analogy with the molecular system is basically it's like a triplet state.
Oh yes, thank you. So thank you, Professor Samanta, for such a nice presentation.
Yeah, sorry. Initially it was a problem, but then now I feel.
Professor Misra, I think there are just a couple of more questions in the chat box.
Okay.
Oh, there is one more question. Professor Samanta, please.
Yeah.
So one question from Parijat Sinha. He asked that how can we know whether the trap state are deep or shallow state using FCS and blinking properties?
Well, I think from FCS, I don't know how to do that. But if you are doing the experiment in the solid state, then there are ways. Different natures. I did not go into. I had a lot of data. I would suggest the person to look into some of our recent papers, where we have found out basically three or four different factors. Say, for example, hot hole capture. It's a basically competitive non-emittive process. Any competitive non-emittive process will give you blinking or fluctuations. Now that can be a hot hole capture. Hot hole does not come to the ground level of the conduction band. That can be one state. And if there are shallow trap state, if there are deep trap states, all will contribute to this, and they can be identified because it's not a very straightforward thing. Multiple analysis, and I think I showed that by blinking and the diagram, the intensity versus time trace. I divided vertical axis. I divided into 4 different segments, and I drew basically intensity versus time plots. Now, and analyze them very carefully, and to come to the conclusion, what is the nature of the trap state. Yes, they can be identified.
So one more question, Professor Samanta, please.
Yeah.
So by primarily, she asked, I think, is there a substitute instrument if there is no fluorescence spectroscopy present?
If there is, what is that?
Is there a substitute instrument if there is no fluorescence spectroscopy present?
Well, there are many other spectroscopic, instruments. Say the limitation and the positive aspects of the fluorescence spectroscopy is that a very small concentration, very dilute solution can be used for measurements. You can detect, as I showed, that even a single molecule. But there are many other techniques. The molecule is not fluorescent. There are many. Most of the molecules are non-fluorescent. And obviously, you cannot use fluorescence spectroscopy to study them. Only when the molecule is fluorescent, you can use fluorescence spectroscopy. If the molecules are dark, like benzophenone, there is no way you can't see the fluorescence, and you can't get. Obviously, you cannot extract anything from fluorescence spectroscopy. So there are many, all IR spectroscopy. There are many spectroscopic technique. Much more used, like NMR. I would say for organic chemistry they use. The problem is that they are not as sensitive, but then I think they are quite versatile. They are much more useful from the use point of view. I would say, NMR and etc. are more versatile and useful compared to the fluorescence spectroscopy.
So thank you, Professor Samanta.
Okay.
So our next speaker is Professor Nilmoni Sarkar. So now about Nilmoni Sarkar. Professor Nilmoni Sarkar is well known among the chemical science fraternity for his contribution in the field of fluorescence spectroscopy. After completing his PhD research under Professor Konkan Bhattacharya at IACS Kolkata in the year 1995, he moved to Japan as a JSPS postdoctoral fellow and then joined as assistant professor of chemistry at IIT Kharagpur. Presently, he is the professor of chemistry at IIT Kharagpur. So according to many of us, Professor Nilmoni Sarkar initiated research in fluorescence spectroscopy at IIT Kharagpur, and now he took it a new high to attract both researchers and scientists to carry out research in fluorescence spectroscopy at IIT Kharagpur. He has a very productive lab and is to publish quality research articles in high recognized journals in his field. So one of his articles in Chemical Physics Letter has been awarded as most cited article in the year 2003 to 2007. And as recognition of his excellence in research in physical chemistry, Professor Sarkar has been nominated as a member of the editorial board of Journal of Physical Chemistry for 2018 to 20. He also elected as a fellow of National Academy of Science 2018, and his present research interest involves picosecond time resolved fluorescence spectroscopy, fluorescence correlation spectroscopy, and fluorescence lifetime imaging microscopy to probe the structural dynamics of different self-assembled organizations. So with these few words, I request Professor Nilmoni Sarkar to deliver his lecture.
You can see my screen, no?
No, we cannot see the slide.
No.
No.
Maybe Professor Samanta has to stop his because his presentation mode is still showing on the screen. I'm not sure.
Can you see?
Now it's come. Yes.
Coming. Now it is coming.
That is coming.
I once again request everyone other than the speaker to mute your device, please. I request everyone other than the speaker to kindly mute your phone device. Kindly cooperate.
You can see the screen, no? Okay.
Your PowerPoint presentation hasn't come. It just says you are presenting, at least for me.
Is it coming?
I don't know if, your slides cannot be seen.
Not seen. Don't know what is happening.
You have to share the correct screen. Just keep your presentation open in the background and then present now. It says Nilmoni Sarkar is presenting, but you have probably not clicked on the window.
Yeah, you have shared your entire window. Instead of that, yeah, because we see it is your inbox and meet and everything is visible. Just
a minute.
Yeah. You open your. I know. I know you are well conversant with, but just please don't take it otherwise. You just open your PowerPoint. And then present window. I think it should work.
Can you see?
No, it is sharing your screen.
It's zoomed too much. You have to control minus sign. If you press, maybe it will get smaller.
It is. Can you see it, or it is?
No, we can see a part of the screen, not the whole thing. So you have to click control minus sign to reduce the size so that it comes to regular size.
It's coming now?
No.
Sir, it's Siddhartha. Sir. Sir, please stop sharing and then again share, minimize the window and maximize the PowerPoint.
Okay. Stop sharing.
Start sharing and minimize the Google Chrome window and maximize the PowerPoint.
Sharing should be window, no?
Yes, sir. Start sharing in Zoom. That is present now. Present now. Then minimize the Chrome and maximize the PowerPoint. And right, it's okay. Now it's okay.
Now you can see?
Now,
yeah, now it is visible.
Okay.
Now you can go to your PowerPoint presentation and you just go slideshow.
Okay. Can you see now? Clearly?
Yeah, perfect.
Perfect. Yeah.
Okay. Sorry for the inconvenience. Good afternoon, everybody. This is a privilege for me to present some of our fluorescence fluorescence aspect actually in this fluorescence spectroscopy colloquium basically. You have heard a very interesting lecture, a very advanced one by Professor Anunay on single molecule spectroscopy actually. Because as we all are speaking on fluorescence spectroscopy, something maybe some overlap should be there actually some way, but I try to minimize as much as possible. The title of my talk is A Journey in the World of Fluorescence, Basic Concepts with Advanced Application. So far, as per the audience, actually, there are many university students, many college students, they are attending this colloquium, actually. So, first of all, I would try to give some basic aspects of fluorescence, which maybe in some those who know it may be repetitive, but still, I would like to share these things, and then I will share with respect to advanced application. We will share some of our experimental data with you. So if you consider fluorescence, it is a branch of spectroscopy, and basically spectroscopy means it is a light matter interactions. And whenever you are considering light matter interaction, there are one thing, if a molecule can, with light matter interaction, it can absorb light, and when it absorbs light, it can go to its excited state, and it gives a general process that is called the luminescence. And another thing also may happen, that whenever we are considering light matter interaction, there is another phenomena that is called scattering. And with respect to scattering, the one of the very important discovery was done from our country, that is bearing the name of Professor Raman, that is the Raman effect. And if you consider the discovery of Raman effect, it was there was a confusion, because whenever you are measuring fluorescence, it can come. Actually, this Raman scattering is always come. So sometimes it is considered as a delayed fluorescence initially. And that's why there is a confusion when Raman discovered this Raman effect. He was also not sure that whether it is delayed fluorescence or it is really a scattering phenomenon. Okay, so there are many types of luminescence, actually, according to like chemiluminescence, crystalloluminescence, electroluminescence, mechanoluminescence, bioluminescence, as well as photoluminescence, radioluminescence, and thermoluminescence. Mostly, actually, we are interested in the thing that is called photoluminescence. And photoluminescence has two things, actually, two parts. One is both are radiative process. One is fluorescence, and another is phosphorescence. So, if you consider fluorescence, then with respect to fluorescence, if you see this molecules, actually, any problem?
No, you go ahead.
No, please continue.
Okay. So you can switch. You can switch from this molecule to pyridine-1, and what you see that there is you can get a interchange in color from say UV to up to visible region. And as for example, if you consider phosphorescence, this molecule is non-fluorescent, not giving any phosphorescence, but when you rigidify this molecule, you can get phosphorescence. So rigidity in the matrix or rigidity in the molecule is one of the criteria for getting phosphorescence. This is an example of phosphorescence where you are getting this at room temperature. And if you, with respect to fluorescence and phosphorescence, these two things are important because fluorescence occurs in a much faster time scale and phosphorescence is a delayed process, actually. Now, if you consider the brief history about fluorescence spectroscopy, it was first discovered by Professor William Herschel in 1845 in a quinine solution, actually. This is taken from this YouTube picture, actually. You can see blue fluorescence is coming from this quinine solution. And whenever you are just blocking this with your hand, this light is going off, actually. That means this UV light is exciting this molecule that is coming from the sunlight and giving this beautiful blue fluorescence. And another thing, if you consider with respect to very important phenomena that is called the Stokes shift, this was also in that way it was discovered accidentally. This is a quinine solution kept in table. Actually, quinine solution is normally known as tonic water. It was used, people are taking earlier days very much to prevent from malaria, actually. So the sunlight is coming and it is shining this quinine solution. So, from this quinine solution, the blue fluorescence is coming. And there is a yellow glass of wine actually here, which is acting as a filter. It can cut light up to 400 nanometer, and this quinine is giving fluorescence above 400 at the blue region. So it acts as a filter, and he is observing the fluorescence, the blue fluorescence through his eyes. So there is a huge difference in the absorption and emission, and this difference in wavelength, which is commonly known as Stokes shift, according to bearing the name of Stokes. Next, the famous thing with respect to fluorescence that we normally consider, that is called the Jablonski diagram, according to the name of Professor Alexander Jablonski. Alexander Jablonski actually is associated with the University of Poland, that is the Warsaw University. He is basically born in Ukraine, and mostly this Jablonski diagram and many related fluorescence-related work actually done in this Warsaw University. He has a, very good violin player, as well as he took part in both the World War, First World War as well as Second World War. And at that time, his research was severely disrupted, but still he continued his research and give this beautiful thing actually. That is the Jablonski diagram. Within this diagram, one can explain the different radiative as well as non-radiative processes. So if you consider this is the ground state, ground electronic state with several vibrational state, level with say 0, 1, 2, and this is the first excited electronic state with different vibrational level. This is the S2 state, second excited electronic state. It may have upper excited electronic state also. So whenever you are exciting a molecule, you get sufficient energy, so it can go to S2 or S3 state. And ultimately, it is coming down to this ground vibrational level of this first excited electronic state by internal conversion as well as by this vibrational relaxation. These two processes are very fast processes, and it dissipates excess energy through heat or some way, and it comes down to this state. This is known as actually Kassa's rule. It was proposed by Professor Michael Kassa in 1950. This rule states that fluorescence is always originating from this ground vibrational level of the first excited electronic state. And if it is true, then there should be no wavelength dependency on fluorescence. Wavelength dependency means there should be no excitation wavelength dependency on fluorescence. One should get always fluorescence from this ground vibrational level of the first excited electronic state. And if there is no geometry change in the molecule in the excited state, one should get also another important property, that is the mirror image relationship between absorption and fluorescence. And there is another thing, that is the non-radiative process. One is taking place between this same multiplicity state, S1 and S0, that is internal conversion. Another is a non-radiative process, that is intersystem crossing, by which this triplet state is populated. And singlet to triplet transition, this is a thin forbidden transition. So normally it is a non-allowed transition. But still we are observing this phosphorescence process. So how it is occurring? Because whenever you are considering this process, this triplet character actually, it is not a real triplet. Through spin orbit coupling, this triplet identity has lost. So it is a mixture of singlet and triplet state. In that way, in that case, this spin forbiddenness has gone, and one can populate this triplet state. There are other factors also. This spin orbit, it is related to spin orbit coupling, and as well as this triplet state population is related to the energy gap actually. So, and if you see that normally one can get fluorescence from the S1 state, but from higher state also, S2 or S3, one can get fluorescence. How it is possible? It depends upon this energy gap actually, because this non-radiative rate is related to the energy gap like this actually. And regarding non-radiative rate, there are many theories. One is famous by Professor Elsoid. And in general, there are some, I write it as a constant, but there are some other factors. It is not really constant actually, and it is related to the exponential energy gap actually, delta E by RT. So if you have a larger energy gap actually, as for example in case of azulene type of molecule, then your non-radiative rate will be not fast, it will be slow. So a molecule can stay sufficient time in the S2 state, and one can observe fluorescence from the S2 state also. That is possible. And in today's concept, actually, if you consider, nowadays one can monitor any process at a very fast time scale, up to say a few femtosecond time scale. So it is possible to observe fluorescence from upper state also if you have a proper measurement system. So if you consider the Kassa's rule, in general, Kassa's rule is valid, but with respect to some restrictions. Okay. So there are many factors which are affecting fluorescence. These are the factors: temperature, solvent polarity, viscosity, Another thing, solvation or solvent relaxation, conformational change, rigidity, internal molecular charge transfer, proton transfer, probe-probe interactions, change in radiation-less transitions and other things actually. So I'm not going to discuss all these things actually. I will just emphasize on this one of the very important factor, that is the solvation. Because whenever you are changing the solvent, one can observe the solvent-dependent fluorescence. These are some examples you can say from a non-polar solvent to polar solvent. There is a change in a huge Stokes shift one can observe actually. So, as for example, whenever you are consider this Jablonski type of diagram actually, in a less polar solvent, it is not this state is not stabilized, and when you consider a polar solvent, the state is more stabilized due to the effect of the solvation. And so this energy gap is decreasing, and one can get a red shift in your emission spectrum. And that can happen in a series of solvents, depending upon your polarity. You can move from, say, very blue region to a red region. Okay. So far we discussed, mentioned that according to Casa's rule, there should be no excitation of length dependency on fluorescence. This is not correct actually. Later, actually, Giorgio Weber in 1960 in a biochemical journal, he published some data actually, and it shows that this is true actually. Emission spectra is independent of excitation wavelength. This is true only for fluidic solution. But if you are taking a sample in a very viscous sample or in a rigid environment, in that case, one can have the possibility of excitation dependent emission. As for example, if you consider this situation, this is a two-state model to explain this fluorescence phenomena. So the Ks, it is the rate constant for, say, solvation. And this is the, whenever you are exciting at the rate edge of this excitation spectra. And this is the rate edge emission actually. So there are three situations. One is when your solvation rate constant is much lesser compared to your fluorescence lifetime or fluorescence rate constant. Another case is when your solvation time is much higher compared to your fluorescence lifetime. Another thing, when these two are comparable. Actually, when these two processes actually solvation as well as fluorescence are comparable, then one cannot in a rigid or fluidic solvent. In that case, it is possible for you to observe this wavelength dependent emission. I mean, excitation wavelength dependent emission. That is a special situation. In general, you cannot, but in this special situation, one can, due to these reasons actually. And I'm giving you some example for this radiation excitation shift. This is a very popular molecule that is called ANS, 1,8-anilidonafthrin sulfonate. And if you take at a 1 propanol at 77 degree Kelvin temperature, so it is almost a frozen solvent. And with respect to excitation wavelength, you can see 308, 410, and 420. You can get excitation dependent emission. As well as one can have a temperature dependent emission spectra also with respect to excitation wavelength. And as I mentioned that in case of viscous solvent, one can have this type of phenomena. This was reported by Professor Samanta and his group in 2006 in case of a room temperature ionic liquid. This is a BIMIN PFCX. Room temperature ionic liquid, it is constituted of cation and anion. And the beauty is that at room temperature, this is a liquid, but with a very high viscosity. So if you take, he observed that with respect to excitation wavelength, you see that the emission spectra is changing. So depending upon your, one thing is temperature as well as the changing in the solvent, viscous solvent, one can have excitation wavelength dependent emission also. That is called rate edge excitation shift or REES. This is a very popular phenomena in fluorescence. Now, if you, whenever you are considering about fluorescence, then obviously the fluorescence probe or fluorophore will be very much important. There are two types of fluorophore. One is we call the intrinsic fluorophore, which has inherent fluorescence within the molecule. Another is the extrinsic fluorophore, where the molecule doesn't have fluorescence, but whenever you are embedded this molecule in your system, it can give fluorescence. As for example, many things, and yes, for example, NADH, flavins, chlorophylls, they have inherent fluorescence, as well as most of the aromatic amino acids, that is the L-phenyl, alanine, tyrosine, tryptophan. These are the three popular amino acids. They have a natural fluorescence. These are the extensive fluorescence probes, some coumarins, rhodamines, and many. Most of them are mostly, most probes are basically extensive. Now, whenever you are considering about fluorescence spectroscopy or fluorescence technique, there are two types of measurement. One we call the steady state measurement, when we are not getting any time dependent information or time dependency in our fluorescence data. And another thing is the time resolve measurement. There are several techniques depending upon your time resolution. One is called the time correlated single photon counting, called TCSPC. Another is the fluorescence half conversion. Whenever you are not measuring in a short lifetime or fast lifetime using your TCSPC, then you have to move this technique, that is the fluorescence half conversion. And another two techniques which are used, which is explained detailedly by Professor Samanta regarding this fluorescence correlation spectroscopy or single molecule spectroscopy. And another thing is also there, that is called the fluorescence limiting lifetime imaging microscopy, where you can select a portion of if you have a heterogeneous system or heterogeneous molecule, you can selectively concentrate on a part of a molecule and get information about the lifetime of the molecule and that particular part. So it gives a very important information about that type of system. So steady state fluorescence measurement, so basically steady state refers to the time independent spectral feature and no time related information, and that is emission spectrum is function of only intensity and wavelength. So this is the basic design of a steady state fluorescence spectrophotometer. You have a light source, then you have an excitation monochromator, then you are using a beam splitter to divide your light into two parts. One is passing through your reference cuvette, another is passing through your sample. And then you are using another emission monochromator, and then you are collecting your fluorescence through your another detector. It may be mostly a photomultiplier tube, and then it is basically synchronized with your PC. So if you consider normally with respect to light source, normally we have used a xenon lamp because it can cover with respect to excitation source the entire range. Starting from 190 to 900 nanometer, one can excite any kind of sample. Nowadays, one can use, instead of xenon lamp, one can use these different types of light emitting diodes which are available. So, but one can use a range of LEDs or independent LEDs one can use. And the resolution of emission spectrum will be depending upon the resolution of your emission monochromator, and that will be also depending upon the resolution of your the rating, which is the heart of the monochromator. So, as for example, in a spectroscopic measurement, if your resolution is 0.1 nanometer in some instrument, it is 1 nanometer. So 0.1 and 1 nanometer, this 10 times difference actually that is arising about the resolution of your grating as well as the choice of the slit width. When the intense as well as exit slit in your emission monochromator is very much important whenever you are resolving any emission spectrum. Okay, so this is the much detailed picture actually. This is I am taking from this Lakov's book. You can see the same picture actually, that you are using beam splitter and one part is going to your reference cell, another part is passing through your sample and ultimately coming to emission monochromator and photomultiplier tube. And this is synchronized and it gives rise to your emission spectrum like this. And this is the image of a commercial spectrophotometer. So this I have already mentioned actually. And whenever you are taking some emission spectrum, one thing is important, that suppose you are exciting at 300 nanometer. So you should scan your emission spectrum from 310 or 320. And you should stop 10 or 20 nanometer before your excitation wavelength. Suppose if you are exciting at 300, then you should stop before, so your double of this wavelength should be 2 times excitation wavelength will be 600 nanometers. So you should stop at 590 or 580. Why? Because it is a trivial phenomena. Because whenever you are exciting through some light, this is the gating property that the second order light will be generated. So 300 nanometer light, the second order will be 600. So that is, you get a very nice signal at that, and it will mask all your fluorescence data. But that is not the correct thing. But even nowadays, those who are not normally using fluorescence, but sometimes using fluorescence, because it's a very easy technique. And if you see in a particular institute or a particular department, maybe more than 50% people are using this fluorescence technique. But even I have seen in many papers, in very good journals, they reported this data and that is interpreted that is a fluorescence. So please be careful about this actually. Okay. Another thing very important whenever you are doing fluorescence measurement, that is called the excitation spectrum. Because whenever you are getting emission, so for if you keep your excitation monochromator moving, keeping your emission band there, then what you will get? You should get some feature just like your absorption spectrum. And if your absorption and emission, if there is no geometry change in the molecule, then you should get a mirror image type of relation in molecule. As for example, if you consider pyrene, in case of pyrene, you will get this type of mirror image relationship because there is no change in the geometry of the molecule in the excited state. But if you take a phenol, say as for example salicylic acid or salicylaldehyde type of molecule, then this thing will not be there because there will be a pH dependency and other things. So you will not get mirror image relationship in this type of molecule. Okay, and one thing is very important, the excitation spectrum, because if your excitation spectrum is matched with your absorption spectrum, that means your sample is pure. I mean, fluorescence is pure. Otherwise, you are getting fluorescence from some of that impurity, because this is a very fundamental thing whenever you are dealing with basic fluorescence. I will give you another example. This is a data actually from when I was a PhD student. This is a work of Professor Kankan Bhattacharya from ISCS, and this is a work of my friend Kaustubh actually. We are the co-author. This is the work from his thesis. He is no more, but this is a very nice work. If you consider this molecule actually, this is called benzimidazole, 2,2-hydroxyphenyl benzimidazole. You can synthesize this compound very easily. So there are two types of conformer, OH is in this position and OH in this position. So these two conformers are there in the ground state actually, and one can have proton transfer only from this geometry. From this geometry, the proton transfer form is not possible actually. So if you consider this is the normal emission one can get from this molecule, and this is the proton transfer form actually. And now if you take the excitation spectrum from both this band actually, then you can see this is the absorption spectrum of this molecule, this thing, and this is the excitation spectrum of the proton transfer form, and this is the excitation spectrum of the ground state form. You can see these two are not matching actually. So one can see this is not an impurity, but this is these two rotamers actually. They are you cannot distinguish the rotamer in the ground state because only at room if you go down to low temperature, you can see 77 degree Kelvin temperature. These two bands intensity are reversed actually. So one can check that whether your compound is pure or not, or even one can detect a rotamer by this type of very important information by excitation spectrum. So one should check always the excitation spectrum whenever you are doing the measurement on fluorescence. So with respect to steady state fluorescence, these things one can also do. Stern-Volmer equation one can use to find the binding constant. Another is the Benson-Intervention equation. This is also very important. So with respect to time resolve measurement, actually, there is a gradual change in time scale. If you see this Nobel lecture from Ahmed Joel, you can see that is one can start from say millisecond, and now we are reaching the order of femtosecond time scale. So basically, this is a branch of spectroscopy which is called ultrafast. This is ranging from picosecond to femtosecond time scale actually. And why it is this range? This phenomena is important. If you consider the transition state. Normally in our textbook level knowledge, that transition state is basically a hypothesis. But due to the development of this femtosecond spectroscopy, you can say this is a reality actually. So if you consider the change in internuclear separations for a chemical reaction near about 10 angstrom, and this is the typical molecular speed. So to time required to cross this distance actually near about in a very few picosecond or 1 to 10 picosecond time scale, which you cannot imagine at the time of Arrhenius when he proposed this barrier concept actually. But nowadays one can even for Diels-Alder reaction type of things, one can it was already demonstrated that one can monitor this activation pathway very clearly through this time resolved fluorescence as well as other types of techniques also. Sorry. With respect to time resolved technique, the most important is time correlated single photon counting. So you just excite your sample with a laser, and then this is the electronic system which was basically used by this nuclear scientist. It is a nuclear instrumentation actually, and nowadays used by everybody, the chemist as well as the physicist. And there are two parts. One is you are using two things. One is called stop pulse and start pulse, and which is coming through to CFD and ultimately through a time to amplitude converter, one can measure the decay. So I'm not going through these technical things in detail. So one can, the limitation of this technique actually, this PCSPC, that one can go up to say around 40 picosecond time resolution. If you have a very good detector, that is microscreen plate photomultiplier, and as well as a laser of say whatever the laser, but one can be, as your detector resolution is about 25 picosecond to 30 picosecond, one can measure lifetime of the order of that. So if you want to measure some lifetime below that, actually one cannot use this technique actually. It is not possible using this PCSPC technique. And what is the advantage of measuring this time resolved decay? So advantage is that one can, if you have a, one can have this type of a equation, and from this one can measure the decay. And if you have a say tryptophan molecule residue within a protein, actually, say suppose this is both this residue has a 5 nanosecond lifetime. But whenever you are using a quencher, then the quencher will be accessible to the tryptophan which is outside. So this tryptophan lifetime will be quenched and the other one will not. So by measuring lifetime, actually, it is possible for you to distinguish these two tryptophan, which you cannot do by steady-state measurement. So another thing, normally we can consider this decay rate law by exponential rate law, and if you just simplify these things, it will be generally one can write by this type of multi-exponential lifetime actually. And depending upon if alpha is equal to 1, it will be single exponential, it may be 2, it will be bi-exponential like this actually. Another aspect is also important, that is called the anisotropy measurement, which gives rise to the orientation of these different types of molecule actually. So normally we excite by L format orientations, and with respect to L format orientation, it is possible for you to measure the anisotropy, which is defined by this. Right? This is the vertical polarization, this is the horizontal polarization, and G is the instrument factor actually. And using this anisotropy also, it is possible for you to distinguish both monomer as well as tetramer. So both monomer and tetramer has different types of anisotropy, as you have seen from this rotational anisotropy analysis. One is showing 20 nanosecond, another is showing 5 nanosecond type of lifetime. Okay, so this is one more data. Actually, this is for us. Actually, this is in a reverse micelle. Actually, it is possible for you to distinguish, as for example, the N-heptane is the bulk solvent, and the water is the inside. And with respect to change in W0, this N-heptane component is fixed, and the water component you are getting by exponential relaxation or rotational relaxation one can get. Another thing that with respect to time resolved measurement, that is the fluorescence subconversion. And fluorescence subconversion, this is basically we are using a phase matching conditions. Actually, you are overlapping your fundamental light and as well as the fluorescence light in a crystal actually. So there is no use of electronics actually, and in that case, one can plot intensity of fluorescence with respect to delta T. And in that way, one can reach the, or one can overcome the time resolution of 30 picosecond. One can go beyond that, and using upconversion, it is possible to reach near about 100 femtosecond time resolution. And how this is done? This is the your BBO crystal, and where you are overlapping your laser as well with the fluorescence, and this upconverted signal is generated here. This phenomena was basically generated by an Indian, that is Jagdeep Shah and C.V. Shank. This is a PRL paper, and it was initially and further a review in quantum electronics by Jagdeep Shah. So with this important technique, some Indian's name is also there. Normally it is not recognized. Time resolved emission, I have already mentioned this example, so I don't have time. Fluorescence spectroscopy, that has one can measure a molecular information at a single molecular level. That is discussed in detail by Professor Samanta. I am not going to discuss. What are the two important things one can get? One is the diffusion parameter, he has already mentioned. Another thing is the hydrodynamic radius. These two things actually one can measure. Other important information also one can measure. but these are the two important information one can measure from FCS data. Another is the fluorescence lifetime imaging. Fluorescence lifetime imaging is basically you are attaching a FCS instrument with a time-correlated single photon counting apparatus, so that one can image the lifetime of a particular, when you are focusing your sample, maybe a biological sample or a heterogeneous sample or a organized sample, maybe a protein, maybe a micelle, maybe other types of sample, and maybe lipid, vesicle, and one can monitor the lifetime at that particular focusing point actually. So a particular point, one can have an idea about the lifetime of this. It is not an for the whole sample, but for that particular region. So one can get microscopic images, microscopic picture, as well as the lifetime information of that particular location. Okay, now for maybe for another 5 to 10 minutes, I will give some example of our experiments with what we are doing. One thing we are doing with many things with, say, vesicle, lipid vesicle actually. What is lipid vesicle? From the biological point of view, vesicle is an intra or extracellular organized structure that consists of a liquid or cytoplasm and enclosed by lipid bilayer. So if you have an amplified molecule that saves the assembly and gives rise to this type of structure. So biomembrane is a selectively permeable membrane, and that forms intracellular components like this. Lipid membrane is mimicking biomembranes with respect to structure and function. Water molecules orientation in the lipid membrane interface determines the hydration force. That is very important to knowing the hydration dynamics. So this is some of our data that how fluorescence spectroscopy can be helpful. This is a very common molecule, say coumarin 1,553. When it is if you are considering only vesicle, and then you are adding some additive, that is the phenylalanine, how it interacts with your lipid bilayer, that you see that there is an increase in the intensity of fluorescence. Similarly, whenever you are considering, say, DMPC vesicle, we are using this coumarin 153 as a probe, and in that case also, in presence of sugar, you can see there is a shift. This is the common sugar, maltose, trihalose, and sugar, sucrose. There is a shift in the emission spectra. So one can use selectively fluorescence spectra to monitor this type of interactions. This is another example. Say if you consider this is arginine cap gold nanocluster. We have synthesized this type of gold nanocluster actually, and these gold nanocluster are very small size nanoclusters, and they have shown different types of luminescence property. Different color luminescence property. One can go up to green fluorescent nanoclusters also, using this arginine cap gold nanocluster. We have also used another thing, that is the graphene oxide we have used, and we modified graphene oxide by some synthesis protocol with copper embedded. We have changed the graphene oxide, and then we are sensing some molecules. Say we can sensing adenine actually by this type of nicely synthesized material. And these are some characteristics of this type of material. As for example, if you see this arginine cap gold nanocluster, they have so a huge shift in the emission spectrum like this, as well as if you consider some anti-cancer drugs, as for example doxorubicin hydrochloride, with respect to change in pH, how their fluorescence spectra is changing, that is shown in this picture. Similarly, one can see the interaction of graphene oxide with coumarin. In that case, one can see the quenching of fluorescence in presence of coumarin 343. One can sense modified graphene oxide in copper complex, which is sensing used as a adenine sensor. This is the picture actually. One can sense reasonable amount of adenine using this material. Another thing, we are working lots with different types of vesicle. So we are considering these two vesicle, LAVC, DMPC, and we are working with some self-penetrating peptide. That is arginine like R9, and we are using these two probes, C153 and DCM, common fluorescence probe. So one can see the interaction actually, and one can have an idea about the lipid membrane permeability using this beautiful method and this how this self-penetrating peptide penetrate the lipid bilayer, LAPC, and as well as the other, that one can have an idea from this. This is another example. Say if you consider these two things, actually L-phenylalanine, another this isomer, that is the 2 enantiomer di-phenylalanine. So these two things, if you consider these two things, two additives, one can have this is the how this when it interacts with the vesicle, how this solvent correlation function is changing. This is for neat LAPC. This is LAPC with 12 millimolar L-phenylalanine, and this is with the presence of both actually. So whenever using both A, D, and L, there is a the rigidity of this environment is increasing actually. That one can have from this lifetime data actually. So what you can, this is also further confirmed from our anisotropy data also. You can see here the anisotropy data is less, and whenever you are considering both, actually this anisotropy data is increasing. This is also true whenever you are considering different types of mixed vesicle. As for example, we can consider two mixed vesicle, DMPC and LAPC, and this type of mixed vesicle whenever you are considering actually. So rigidity of this vesicle is increasing depending upon the mixing of these two types of vesicle at different ratio. So I can show you that. If you consider that the more asymmetry in the lipid bilayer due to the presence of unsaturated phospholipid LAPC in 90:10 ratio, and the presence of unsaturated fatty acid makes the bilayer DMPC much less rigid than bulk. So that is possible actually, depending upon your system, choice of system, one can monitor the fluidity or rigidity of this lipid bilayer. Another thing one can, this is the time resolved data, this binding interaction study we have already mentioned about this JVM copper cluster, as well as one can monitor the curcumin interaction, this very famous molecule curcumin, which is available in turmeric with silver nanocomposite, that is possible. And another, this gold nanocluster one can also use for temperature sensor actually. This is, one can use as a, for thermometry actually, temperature dependent emission decay, one can use as thermometry also one can use. This is the another important example, that is the DMS water binary mixture actually. This is a very important solvent for biological system, and it shows some non-ideal behaviors, and there are two regions which was detected by simulation, further by experiment also. It's simulation, it was predicted by Professor Bagchi. These are the two regions of this mole fraction. One is 0.1 to 1.17, another is 0.26 to 0.34. And so there are two things actually, DMSO from hydrogen bonds with water in the form, this one DMSO, 2 hydrogen and water, and another is the water rich region where 2 DMSO and water, 1 water in the DMSO rich regions. And we have done actually using this 5-fluorouracil, this is with respect to hydrogen bonding, the interaction parameter is changing. And how it is, this interaction parameter is changing in DMS water solvent that we have investigated with respect to different DMS ratio. And this is a very important data because this is the third harmonic excitation using fluorescence subconversion. So this is 267 excitation. This is a very difficult experiment actually. And this we reproduced many times actually. And we can give very important information that whatever the different regions we are observing from other experiment, actually this is not reflected in this particular experiment, but it is verified from other cases also. This I am not talking about this fluorescence. This is already mentioned by Professor Samanta in detail. And another thing is this fluorescence lifetime imaging microscopy. This can be used as, for example, fibrilla sample, this type of structure. Actually, one can monitor by this type of lifetime imaging microscopy that one can do by others. Say, you can use FECM and or same for this type of structural investigation also. And determination of alteration properties of the material in presence of the foreign substance. As for example, if you consider lipid membrane and if you add, say, L-phenylalanine actually, then and D-phenyl, you can see there is a change in the lifetime distribution. So this is very important information one can get from this lifetime imaging microscopy. Also, one thing, the self-replication, because if you consider the original life, that is the reproduction system, that is the self-replication we generate the cells. So one can monitor the life tracking. We have done this for fatty acid vesicle, and this is the live imaging. Actually, one can monitor how these two vesicle fuse to generate another vesicle that one can monitor in a real time using this fluorescence emitting imaging microscopy also. Another thing is the fluorescence anisotope imaging. This is a very good technique actually, and it is one can use to be satisfied with respect to this imaging. One can have done also anisotope imaging to get a better picture of this type of system also. So overall conclusion, one can have an fluorescence scan in an important photophysical property of a molecule that occurs in a very fast time scale. So some sophisticated instrumentation is required so monitor this photophysical property. Normal instrumentation, steady-state instrumentation also give a lot of information. Some common measurement technique like steady-state and time-resolved fluorescence measurements, as well as some advanced technique, say FCS, as well as lifetime imaging we have already discussed. And this basic and advanced application in this spectroscopic technique have a new application in this particular area. So these are my group actually. These are my previous PhD students. They are at different positions actually in different institutes. This is my PhD and PhD scholars. These are my postdocs who are working with me earlier. Siddhartha left recently actually. And there are many MSc students actually. I didn't take their name actually, but they have contributed immensely. Whatever my actually success with respect to research that is possible for due to my all my passionate PhD as well as MSc students. Some of the MSc students who did MSc project with me in Kharagpur IIT, they have also continued as a PhD student. Many, maybe more than 7 or 8 students who have already completed, and some of them are doing a PhD with me. And before finishing, actually, I would like to show some picture. Actually, I am from an institute which is a historic institute in that sense, because this is the institute where it is related to our freedom fighting, or freedom fighting movement is related to this. Because if you consider this is the old IIT, where the IIT was first started in 1951. This is the old building, and this was the Hijri detention camp at that time, and this was the second detention camp after the Boxer in Bihar. So, and you know that this month is also important. Actually, the last week, in 16th September, that was the two freedom fighters, that is the Tarakeshwar Sengupta and Santosh Kumar Moitro. They were shot dead in this place actually by massive firing by the British police. And Netaji Subhash Chandra Bose came here to collect their body, and Rabindranath Thakur attended a public meeting, public gathering in the town hall in Kolkata. So I am from this institute, and this is the prison cells where the freedom fighters are kept. And this is this building now within different color. And this is the old picture with my some 4 students with whom I have started my career here at Kharagpur. These are the different funding agencies: DST, CSR, ACRB, BRNS, FIST, as well as IIT Kharagpur for funding my research. And thank you very much for your presence.
So thank you, Professor Sarkar, for such a nice presentation covering. Hello, can you hear me?
Loud and clear.
Yes, we can hear you, Professor Misra.
So thank you, Professor Sarkar, for such a nice presentation covering the basics of fluorescence and also the TCSPC and upconversions and all the aspects of fluorescence spectroscopy, and also some nice work that we have recently done that is also that we have presented. Now it is the time for question and answer session. If you have any question, you can put it in the chat box. There is one question that I received from Bapaditya Norskor. So what is the advantage of fluorescence over absorbance?
If you consider fluorescence, this is giving you the information of the excited state. And from absorption spectroscopy, you are getting mostly the information from the ground state. So that is the basic difference. There is a question from some high school student, I think.
Yeah, that is, I think, yeah, I can read that one also. By Subhankar Palit. He wrote that, sir, I am just a high school student and could make just a few part of your speech in spectroscopy, the most cutting-edge research topic in chemistry in today's world. Just his actual observation that is given. So I think there is no more question. I have one question to Professor Sarkar.
Please.
As you told, as it is well known actually, the emission mainly comes from the ground vibrational level of the S1 state. That is the Kassa's rule. But in case of carbon quantum dot, the emission depends on the excitation light also. So how do you explain that one?
So, frankly speaking, I cannot explain, and I think in the literature also it is not clear till now. So if you see about carbon dot, this is a very controversial thing till now. And with respect to the origin, actually, whether it is due to molecular fluorophores or due to others, actually, there are a lot of works, but still, it is. I think it is a lot of controversy.
So thank you, Professor Sarkar. If there is no question, so let us thanks to both our speakers in this session, Professor Samanta and Professor Sarkar. So with this, we are just going to conclude this first technical session of this one-day webinar on fluorescence, recent advances in fluorescence spectroscopy. So this is over to Omio Pandya.
On behalf of the organizers, we thank both the speakers and the chairman, Professor Ajay Misra, for kindly taking the trouble to nicely conclude and conduct the technical session 1. And we take the advantage of virtual meeting or the webinar that we can go for any break. We can have virtual break for 5 minutes and we can have our lunch with the meanwhile. So if you kindly agree with us, so we can go for the next technical session. What do you suggest, Professor Misra and Professor Dasgupta?
For me, you mean to go for the technical session right now or have a break? Because Professor, it depends upon the speakers, Professor Dutta and Professor Guchhait. For me, it's fine. But others may want to go for lunch also. Anything is fine with me.
So should we go for a lunch break for half an hour then?
Fine for you.
I'm here.
What do you suggest? Your lecture was supposed to start at 1:30. So what do you suggest?
I'm ready, but ekaki gayoker nohe to gaan gaite hobe dui jone. The audience is ready. I'm ready.
But the audience will be ready after. Theoretically, the audience who would want to come to your talk would come at 1:30.
Yeah.
It's 1:25 now.
So we can start at 1:30 if that's fine. I'm good.
Fine. That's fine with me. I don't have a problem at all.
So yeah. I will just put my video and the speaker up and I will have my lunch. No problem.
So,
I hope and the chairperson they have already taken
Ajay. So he looks fine and looks slim also.
Everybody is very curious to know what is the secret. How Dutta has lost the weight.
I didn't recognize your picture. I said, when is this taken?
Yeah.
Well, it's good that you asked for a picture so that people got a forewarning.
Yeah, but in the Facebook, when I was following Professor Dutta, then someone from the eastern part of India was making a comment that they are following the less atelier principle, that Professor Dutta is losing weight and the eastern part of India, someone is gaining weight. Am I right, Professor Dutta?
Yeah.
Yeah, you look at me and you'll know the difference.
So in that sense, Professor Anindya Dutta, although he is heavyweight in theoretically, but in reality he is not heavyweight.
Well, all I can say is that I've not stopped throwing my weight around.
Good one.
So next session will be chaired by Professor Swagata Dasgupta. Huh?
Yes, so we'll start exactly at 1:30. Yeah.
Right. No problem.
Okay.
Excuse me a second.
How are things at IIT Bombay, Anindya?
I'm sorry?
How are things there, institute-wise?
Things are fine. Things are fine. We are having a new case every day, apparently. But
Okay.
things are under control. Nobody is very sick, thankfully, except for some people in the beginning. Now things are pretty much under control. Labs are opening one by one.
I see.
What about you people? Have you reopened now?
Not yet. The postdocs have been permitted last week, but the labs are not yet reopened, and classes are like everybody else online.
Yeah, classes are online, of course. How do you propose to do the exams?
Well, there are lots of debates about that. Continuous evaluation seems to be the most accepted protocol for now.
Yeah.
But then the sheer number of students is going to pose a problem. So,
come November, it's going to be even more interesting when first year.
The first year, exactly. So that is what there are lots of debates about how it should be conducted. So continuous evaluation seems to be the way on using Moodle or the standard some software.
We are exploring proctored exams and all. I am not a very big fan of those. I mean, it's too much of trouble for no reason.
Yeah, and there's not much you can do anyway. I don't think it's, given the situation, there isn't much you can do.
True.
Proctoring exams, it's difficult. It's difficult.
So, I mean, good thing is that whatever quizzes we have conducted so far, we have seen good distribution of marks.
With some of these softwares, we have a Moodle setup where you can you can choose from a pool, a question bank, and then So the questions are jumbled, the options are jumbled, and you give a specific time frame. So there's no point in asking anybody else the answer to the questions. So that helps.
According to a colleague, you should give less time so that people are busy solving their own question rather than helping each other. If you give too much of time, that could be an issue.
You lose out. And the ones we usually have for the first year is once you solve a question or you've coded in the answer, there isn't a choice to go back.
Yeah.
So you cannot return to your question. So in that case, it probably works. We've had it with the first year and it's worked so far. But people have to get used to it. That's the major problem we are having is presenting. The first 10 minutes of the class go, can you see me? Can you hear me? Can you see my slides? Can you hear me?
Yeah, so these are the most asked questions in the world today. Am I audible? Can you see?
Can you see my slides? Right.
And maybe
so, Professor Dasgupta is 135.
Yeah, I'm ready. I'm ready.
Yeah, can we start? Can we start then?
Sure.
Yeah.
Okay.
So this session will be led by Professor S. Dasgupta. Over to you.
Okay. A very good afternoon to a very good afternoon to all of you. I guess since we were running out of time and Professor Datta's lectures is scheduled to begin at 1:30. So those of you who are joining now, a very warm welcome to you in this webinar on recent advances in fluorescence spectroscopy. Professor Anindya Dutta from IIT Bombay. He completed his BSc from Presidency College, followed by his master's in Calcutta University, PhD from the Indian Association for the Cultivation of Science, and a postdoc at Iowa State University. Following some other assignments, he joined IIT Bombay since 2002 and is currently the head of the department. He has several awards to his career: the Young Investigator Award from IIT Bombay, Young Researcher Award from the Chemical Research Society of India. He is a Fellow of the National Academy of Sciences and received the CRSI Bronze Medal in the year 2018. His research interests are ultra-fast processes in molecules and materials. He has several PhD guidances under his wings and over 120 research publications. Today, he's going to speak to us on an ultra-fast route to the ultra-small. Professor Dutta, please.
Thank you very much, Professor Dasgupta. Let me share my screen and then I will ask one of the most asked questions.
Yes, we can.
Okay, thank you. All right, I just hope this is the right presentation because there are 3 or 4 open.
Yes, because we saw the conclusion of one.
Yeah. All right.
Perfect. Yeah.
So thank you for having thought of me as a speaker in this very eminent gathering. It is humbling to speak in a meeting where Professor Samanta, Professor Sarkar, Professor Guchhait have spoken or are going to speak. So the good thing about this meeting is that the theme is very well defined, fluorescence, and the 2 stalwarts who have spoken before me have already set the stage so that I am not going to go into too much of basics, but rather I'll try and present some of the results of our lab and discuss some of the problems that we have been trying to address in the last few years. So I'll try and restrict within 40 minutes or less so that if in case there's some question, we can discuss later. I'll start showing you some photographs of our lab. In the previous talk, those of you who were there, you heard about time-correlated single photon counting. Well, this here is the new time-correlated single photon counting setup that we have in our institute, the central facility that we set up last year. And Professor Sarkar talked about MCP PMT detector. This thing that you see here is not an MCP PMT detector. For whatever reason, people nowadays are very reluctant to share technology, but this is what is called a hybrid detector whose performance is comparable to MCP PMT detector without the hassle. If you want to work with a cooled MCP PMT detector, you have to turn on a chiller, you have to turn on Peltier cooler, high voltage, a lot of things. Here, it's plug and play. And what you see on the screen is a fluorescence decay, pretty much like what you saw in the last presentation. Professor Sarkar also talked about femtosecond upconversion. I have learned to be scared to take the name upconversion because the moment you say upconversion, there are so many people working on who make upconverting crystals. They come and ask, can we characterize our samples in your lab? No, you cannot. We use the technique of upconversion to achieve femtosecond time resolution in our experiment. I like to call it femtosecond optical gating. And as you see here, a lot of optics are there, which you need to play around with to get a good signal. For the last 5 years or so, we have also been working on femtosecond transient absorption, which Professor Samanta mentioned in the passing. Here, the good thing about femtosecond transient absorption is that your sample doesn't have to be fluorescent. You can look at a sample that is colored, but not necessarily fluorescent. In fact, fluorescence can be a problem at times. So the good thing is, if you have all these under one roof, then it becomes relatively easy to try and understand what goes on in a molecule or a material after one excites it with a burst of light, a pulse of light. I was thinking of putting in another slide after this, but somehow I forgot. So what we do is that we do 2 kinds of experiments. One is we record absorption and fluorescence spectra, what was referred to as steady-state spectroscopy in the previous talk. The other thing that we do, also referred to already in the previous talks, is that we excite our sample with a burst of light, a pulse of light. What this pulse does is that it creates an excited state population. And after the light goes off, this excited state population is left to decay by itself. And before it decays, more often than not, it does a lot of interesting dances and jiggles and reactions in the excited state that it cannot do in the ground state. And that is what we try to follow in these time-correlated single photon counting or femtosecond optical gating experiments. And essentially, we try to figure out what are the excited state processes that go on in molecules and materials of our interest. So we have looked at a lot of systems in the last 18 years that we have been here in IIT Bombay. Molecules of unusual photophysics have been the topic of our interest for a long, long time. I'll talk about a little bit about those experiments today. More recently, well, we cannot call it recent anymore. It's been 6-7 years. We got interested in exotic nanostructures. We were late entrants in the field after a lot of other people, including Professor Samanta and all, had already done phenomenal work in this. So our work sort of builds upon them, and we try to get into systems that have not been studied earlier. Disilica nanoconjugates and their prospect in light harvesting and artificial photosynthesis has been our dream for the last 12, 13 years. And like any big dream, it has proved to be more difficult than what we thought it would be. So the idea in this problem is this: we want to simulate a green leaf, and that has been done in phenomenal experiments more recently. So what we thought is that we'll use silica, surface of which can be functionalized very easily. Well, we thought very easily. Later on, we understood that it may not be all that easy. So we thought we are going to graft silica nanostructures with energy donors and energy acceptors and see whether we can sort of simulate the photosynthetic light harvesting antenna in this kind of a system. And we had limited success. What you see here is transient absorption spectra of a donor acceptor combined on silica nanoparticles. From this spectra, it is not very difficult to see that energy transfer is actually taking place. But then there are issues that we are not going to talk about today, but there are issues mainly concerned with how you prepare the sample and how cleanly you can do so. It turns out that it makes sense to try and use a smaller population of dye molecules on the silica surface. The problem is, if you use a smaller population, then the average distance is more, and then the molecules don't talk to each other. From there, we got interested in plasmonics, because plasmonics can actually help to be sort of a bridge so that energy donation can take place between molecules that are relatively more distant. So we are trying to learn plasmonics in collaboration with Professor Alison Funston's group in Monash University, Australia. Our student, Bala, has been working on this. And what you see here is gold nanoparticle dimers prepared by Bala. We are studying excited state dynamics of that. It's a new field for us. We're learning every day. Another field that we have sort of gotten into is biophysical chemistry. Again, we want to work in it, but we don't know much. So we have collaborated with Professor Samrat Mukhopadhyay of IISA Mohali and our very own Professor Kamendra Pratap Sharma of our department. And with them, we have tried to follow processes that go on in intrinsically disordered proteins, IDPs, and something very strange called what Kamendra calls waterless protein liquids. So basically what you do is you take a protein, you wrap it with a polymer, which is a liquid, and then you lose water. So you get back a dense solution in which the protein retains its structure, and as we have shown, its function to a great extent, but there is no water. So this is something that is very interesting for people like us who want to study dynamics in systems like this. So this collaboration is also ongoing. We are trying to learn new things in these fields. So today, I mean to tell you 2 or 3 stories. We'll stop the moment we reach about 38, 39 minutes. So I started at, I think, well, we'll see. I think Chair can remind me when I have to stop in 5 minutes before.
Yeah, sure, I'll do that.
Thank you very much. So we start with this simple-looking molecule, simple-looking family of molecules, aminoquinolines, that we got interested many, many years ago, a time when we actually did not have any instrument in our own lab. We used to go to other places and do experiments. I had a student, Devashish Panda, who is now an associate professor in Rajiv Gandhi Institute of Petroleum Technology. He developed a fascination for aminoquinolines for a different reason, but then what turned out was also interesting. So it turned out that these are very strange customers. Generally, if you work in organic molecules that fluoresce, then you expect that the fluorescence is strong in nonpolar media and weak in polar media. Because in polar media, you can get what is called intramolecular charge transfer. This is an excited state process. For students who are new to this field, you might remember that I said that once you create an excited state population, they can do a lot of jiggling and wiggling and dance and undergo some processes before they come back to ground state. So this is one of the processes that can take place. What happens is when you excite molecules, they usually can do things better than what they can do in ground state. Pretty much like us. If we're excited about something that we do it better. Same with molecules. So an organic molecule, which is an acid, usually is a stronger acid in the excited state. An organic molecule, which is an electron donor, is often a stronger electron donor in the excited state. Electron acceptor is stronger in the excited state. So here, what happens is when we excite it, and we'll not go into the reason now, it is now textbook material. Whoever is interested, I recommend that you read this from the classical photochemistry textbook by Professor Rohit Mukherjee or Professor Tua. So what happens is this. Generally, when you work in fluorescence, ICT is a villain. You don't want it to happen. But here, the thing is this, when you work in nonpolar media, this NH2 group can undergo this kind of a Walden inversion kind of flip-flop motion. And that is a very, very efficient non-radiative process that is provided to the molecule. That is why in nonpolar media, the locally excited state decays very, very fast. However, if you go over to polar media, now ICT can take place. Remember, generally ICT is bad news for fluorescence. Here, it is the lesser evil. Because if ICT takes place, then these NH2 cannot wiggle all that efficiently anymore. So it is sort of held in place. So Devashish did a very thorough study of this molecule, 3-aminoquinoline especially, in solvent mixtures, different media, and so on and so forth. And the model that we came up with was, again, it built upon a model of aminocoumarins developed by the group of Professor Haridas Pal of PRC. So, like aminoquinoline, it appeared that here also, the problem is that in nonpolar media, this flip-flop motion takes place. And if ICT is there, then it is stopped. So you get relatively stronger fluorescence, longer lifetime. So that was, as you see, the paper was published in 2006, and almost 10 years passed before another student got interested in this kind of molecules. His name is Avinash Kumar Singh. He just finished his first postdoc in Ames Lab, and he's on his way to Canada whenever the prevailing situation permits him. So what Avinash saw is that he wanted to perform low temperature experiments because there are many questions about whether these processes are activated or what. And he observed some very, very strange observation, something very strange. So he worked with two different molecules. One is 3-aminoquinoline, and the other was a synthetic derivative, which we prepared with help from a postdoc in the lab of our colleague, Professor Devabrata Maiti. So in this derivative, 3PQ, you have ICT all the way. All the time you have ICT. In 3AQ, you can have emission from locally excited state, or you can have emission from the ICT state. ICT state has a red-shifted emission. Now, what happens is this: as we lower temperature, what we see is that even the peak position of 3PQ changes a little bit, but it is not so much. For 3-aminoquinoline, you see an ogive. So there is a clear crossover from locally excited state to ICT state at low temperature. I've not told you which solvent it is. It is a 3-methylpentane, a non-polar solvent. In a polar solvent, it is not all that dramatic. So what is going on here? After we got this experiment, this poor chap Avinash came to my office and said, sir, at low temperature, non-polar solvents become polar. Well, leaving out all the other detail, let me just say that the rest of the evening was not very pleasant for him for having made such a strange statement. That non-polar solvents become polar when you lower the temperature. But then, as Max Planck has famously said, experimental results are the only truth. And I heard this from my PhD guide, Professor Kankan Bhattacharya. Experimental results are the only truth. Everything else is poetry and imagination. We did the experiment 5 times, 10 times. Every time we got this result. So this is the truth. So what is the poetry? What is the imagination? What is going on here? What we feel, we do not have a very definite answer to this. But what we feel is this, that when we excite this, there is a charge separation that takes place in the molecule. And this charge separation would, of course, induce dipoles in the surrounding solvent. In a fluid medium at higher temperature, these induced dipoles can diffuse away very, very quickly, so you don't see the effect. And therefore, the reaction field due to the solvent dipoles on the solute dipole is very transient in nature. Our hunch is that at low temperature, since the solvent is frozen, these induced dipoles cannot diffuse away so easily. So the field is more stable. So when I say field, I mean the reaction field. These induced dipoles that are produced in the solvent as a result of production of dipole in the solute, they now interact with the solute dipole, which was responsible for creation of the solvent dipoles in the first place. At low temperature, we believe these cannot diffuse away. So the reaction field is stabler, longer lived, and that is why we see an effect, a manifestation of it in showing up of the ICT state in 3-aminoquinoline at low temperature in non-polar solvent. But non-polar solvent does not become polar at low temperature. And since there are students, I also want to say is that one has to be careful about interpreting the result. When we interpret the result, we have to be very careful and think whether it is a property of the molecule or the medium or an interaction of the two. If we make an inference that is as outlandish as the one that I said a couple of times already, we could have been in trouble. Okay. So now, then we moved on to a positional isomer, 5-aminoquinoline, which is a little better behaved. And it does show strong quenching in polar solvent, especially protic solvent. So we established the role of hydrogen bonding in the excited state dynamics. I'm just rushing through this part because I want to get to the next. And to cut a long story short, we developed this kind of a scheme of things that happen for 5-aminoquinoline post-excitation, depending on whether the medium is polar or non-polar or protic or what. So this was all Avinash's work. Then he started something else, which he could not finish before leaving for postdoc. This was carried on very elegantly by my student Sharmishta. So the question that we wanted to ask is this. For 5-aminoquinoline, we have a strong emission in and one kind of a lifetime in non-polar solvent, and quenched emission and another kind of lifetime in polar solvent, especially protic solvent. So now, can we study the time? So the whole idea of solvation dynamics is that you want to see how much time it takes for the solvent to react to a dipole that you can create instantaneously. What we thought is that we'll take this 5-aminoquinoline in a non-polar solvent, add very, very small amounts of polar and maybe protic solvent, then excite the probe molecule. And then the question was, do we see preferential solvation? Preferential solvation means, since the molecule is more polar in the excited state, even though we have, say, 0.1% or 0.5%, 0.5%, 1%, okay? That was not a mistake, 0.5%. Ethanol or methanol or whatever alcohol in the system, they would like to come and solvate the molecules. This is called preferential solvation. So what we thought is that if we can study the dynamics of preferential solvation, maybe we can understand how much time it takes for a polar solvation shell to build around an instantaneously created dipole in a non-polar liquid bulk. So this is the idea. This is your molecule, excited. It is, well, surrounded by, say, hexane, non-polar molecules. Sharmishta is responsible for all this fancy animation and interesting font and all that. If you like it, credit goes to her. If you don't like it, that's not my fault. I like it. So when we add alcohol, so these are, say, alcohol molecules, they would like to come and displace hexane molecules in the first solvation shell. And this should be even more when we excite it and the molecule becomes dipolar. Now the alcohol molecules should rush in and try to solvate the molecule. Can we see the dynamics? So we are trying to see a very fine level of microheterogeneity here. And from steady state spectra itself, we can see the microheterogeneity. And when we look at time resolved data, without again going into technical detail, just believe me when I say that using steady state and time resolved experiments, we can actually see how fluorescence spectra evolve over time after excitation by a delta pulse, by an instantaneous pulse of light. And it does evolve from a spectrum that you expect in a hexane-like environment to something that you would expect close to alcohol environment. And we monitored the dynamics of this using tools that I learned as a PhD student many, many years ago of solvation dynamics that has been studied very extensively. So what we see is that we do get a nanosecond dynamics here. And dynamics in tertiary butanol is slower than what you see in methanol, point number one. That is because tertiary butanol is bigger molecule, runs slower. The other thing is, if you look at the initial part, it is sort of convex for methanol. So from here, the model that we build is that when we have that kind of solvent mixture, Professor Sarkar has talked about DMSO water solvent mixture. This is another kind of solvent mixture, methanol and polar non-polar solvent mixture. So here it appears that when we have very, very small amount of methanol in say hexane, they are there as clusters. So it takes some time for them to sort of get rid of the affection for each other, break the hydrogen bonds, get declustered, and then come and solvate this newly created dipole of the soluble molecule. So this is what we learned using aminoquinolates. So that is molecules. All right, the title of the talk is ultra fast route to ultra small. What is ultra small? Well, what can be smaller than atoms and all that? But when we say ultra small, generally nowadays we like to talk about nanoparticles and stuff. So let me now run you quickly through a little bit of work that we have done on cadmium selenide nanotetrapods. One of the reasons that we wanted to work on nanotetrapods is that being late entrants, we found that whatever could have been done in regular spherical nanoparticles were already done. A wealth of information existed. So we thought it makes sense to learn from them and try to look at shapes that have not been studied so much earlier. And well, nanotetrapod is tetrahedral, a shape that all chemists love. So this work was started in my lab in collaboration with Professor Rohit Srivastava of our Bioscience Bioengineering department by an integrated MSc student, Ashutosh. But then it was taken to its completion by my PhD student, Sucheta, who's now an assistant professor in postgraduate college in Pune. Sucheta did her MSc from IIT Kharagpur. And right now, it is being carried over by another PhD student, Faryad. So cadmium selenide nanotetrapods are interesting, except for the shape per se, because several applications in things like solar cell or biosensing as building blocks of inorganic dendrimers and so on and so forth have been proposed. Even yesterday, some paper came out, and there what all they talked about is how promising these are as building blocks for inorganic dendrimers. So since we are doing this for the first time, we had a lot of false starts. We did a lot of stupid mistakes and ended up making nanoparticles that were completely useless. And here we had very valuable contribution from Bala, who I talked about, our PhD student, who's a student of actually IITB Monash Academy. So his degree is going to be from IIT Bombay and Monash University together. So even though Bala was not working on this problem, he had some prior experience from his MSc days. So he sort of corrected some rather naive mistakes that we were doing, and we were finally able to prepare nanotetrapods. And this is what you see under electron microscope. The diameter is something like 2.6 nanometer. Of course, there's a distribution. And arm length that I show here is 22 nanometer, but it varies depending on reaction time. So, and this is the compulsory photograph that you have to show always if you work on our nanoparticles. As we change size, color also changes. But this is actually PL. It's in a photoluminescence. It's taken in a UV chamber. So we could prepare two kinds of nanotetrapods. The first ones, when we did not know how to do it properly, we did it in ambient condition, and we got, in addition to, so see, this is the absorption spectrum. This is, we heard about mirror image relationship. We get one kind of emission feature, which is a mirror image, that is called the bandage emission. And we see a red-shifted emission feature, which Professor Samanta had mentioned. This is called trap emission. There are so many imperfections on the surfaces of nanocrystals. They act as traps and lead to many interesting, sometimes useful properties. So this is what happened when we did the reaction in air. Then, taking Bala's suggestion, we used the glove box. And then we found that you can suppress trap emission significantly, and bandage emission intensity goes up significantly as well. All right. When I say significantly, you might think that it goes up by a lot. If you take the relative amounts, it is a lot. If you look at absolute numbers, when trap state emission is there, then the quantum yield of the trap state is 0.008, quantum yield of the bandage emission is 0.003. That's 0.003 value goes up to 0.08. So more than an order of magnitude increase. If I close one eye, I can always also say 1.5 to 2 orders of magnitude increase. And trap state emission decreases from 0.008 to 0.001, 1 order of magnitude. But then 0.08 PL quantum yield, of what use is it? That is the question. But what we figured is that at least using this, we can understand a little bit. We can learn about nanoparticles a little bit using these not so great nanotetrapods that we have prepared. And this is what we learned. What you see here is, first of all, this is the photoluminescence decay in ultra-fast time scale. This is the photoluminescence decay in long time scale, but the emission wavelengths are different. The top panel is for this kind of emission, bandage emission. You see, bandage emission has an ultra-fast lifetime. In absence of trap states, so in this case, these are color-coded. In absence of trap states, we see a relatively longer decay compared to what you see in presence of trap states. So this faster component, and I'll show you the numbers, we see a component of 8 picosecond for bandage emission in absence of trap states. And we see an additional component, a major component of 1 picosecond in presence of trap states. So it appears that this trapping is very efficient. It works with a time constant of 1 picosecond or so. And traps themselves are actually very long-lived. So you can see the x-axis here is in hundreds of nanoseconds. So one question that one can ask here is that, okay, so your trapping is efficient and the traps are long-lived. So PL lifetime is like tens of nanoseconds, if not hundreds. So why is the quantum yield so low, even for trap emission? The answer is that these are not the only traps that you see. These are radiative traps, but these are really not so clean system. So there are a lot of non-radiative traps. And right now, we are trying to engineer these things and try to optimize the conditions here. So I'll not talk about the pump probe data here, but the crux of the matter is that extremely low PL quantum yield, the reason is also figured out using pump probe, and we want to see what is the way out. One way out that we thought about is that we can dope it with something. The copper 1, for example. This is something that is hackneyed now. A lot of people have worked in this. This is one of the examples, Gambin and co-workers, who worked on copper-doped cadmium selenide spherical nanocrystals. And what they said is that when you put in Cu+, then this whole transfer can take place, and then you get a red-shifted emission, which is of a much larger quantum yield. So now this is Faryad's work. What Faryad could do is that he could modify the synthetic procedure a little bit. And let me say here is that I don't know this synthetic procedure myself. Students have figured them out by themselves. So if there's any question, I'll just pass them on to students. You can write me an email and all, I can find out. All right. So with a little bit of modification, we could prepare copper-doped cadmium selenide nanotetrapods. And now we see there is a red-shifted emission, like what you see for the others as well. And now we see a significantly stronger emission with significantly longer lifetime. Okay. Once again, if you look at bandage emission, we see that so this is for cadmium selenide tetrapods. This is for copper-doped cadmium selenide tetrapods. So once again, we get this 1 picosecond sort of time constant, which signifies trapping that is taking place. Please remember that left panel, the ultra-fast one, is for bandage emission. Right panel is for trap emission. So now we are trying to play around with the conditions. Once again, I'll skip this conversion data. And we are trying to see how we can optimize the conditions so that we can get brightly luminescent nanotetrapods. But these doped tetrapods are much better than other ones. Next thing we wanted to do is that people talk about biological applications all the time of these nanoparticles. So can we get aqueous dispersible nanotetrapods? do that, again, back to Sucheta's work, she and with contributions from another student, Tanuja Kistwal, so they could do a ligand exchange. So first of all, this tetrapod is prepared in organic solvent using a ligand that is soluble in organic solvent, and then it is exchanged with this mercaptopanoic acid, which is water soluble, and now these nanotetrapods become dispersible in water. Great news, but the heartbreak comes in the form that these nanotetrapods are not photoluminescent. We have still done something with it. I'll maybe show you very quickly one slide, half a slide about that later. But then this was really this put us off. And we want things that emit in water. And with some effort, we could make these nanotetrapods that you can actually disperse in water, and they are mute. They don't emit light at all. So seeing all this, yet another student, Sharmishta, and a postdoc, Shomodipto, they sort of conspired, and they figured that they can do better. And generally when people think that way, they are right. So what they have been able to do is, they have themselves come up with this scheme of preparing water dispersible quantum dots, not tetrapods yet, spherical quantum dots of cadmium sulfide, which is coated by polyethylenamine. They have used polyethylenamine of molecular weight 25,000. And the good thing about this is that there's no ligand exchange, no nothing. The entire one-pot reaction is in aqueous medium. So as is depicted in this scheme right here. So there is literature on this kind of work. It is known that colloidal stability is excellent. Surface coverage is good. But it is interesting because the whole thing is in water itself. And I would have said that this is green synthesis had I not known how annoyed some people get if this word green is mentioned. And in any case, we are not green synthesis people, so let's not get into that trouble. This is the electron microscope, what you see there. Let's forget about the crystal planes and all for now. Let's look at the size distribution. The size that they have prepared is about 4.55 nanometer in diameter. Beautiful absorption spectrum that is structured, something that has been observed by other people like Klimov and Kambapati and many other people. And the emission, as you see, so what they have been able to do, what Sharmishta has been able to do is that she has been able to extract the components of this absorption, and she has been able to assign the transitions following standard existing work in literature. And what she has got is something that makes sense. Now, the PL is good. I'll tell you how good. These are all normalized spectra. But one thing that we want to show is that, see, this here is the absorption that is attributed to band edge. And this broad red-shifted band, I'm sorry I cannot tell you which color it is because I'm colorblind, but I think you can figure which color it is. This band is the emission band. And you heard about Kasha's rule. It's expected to be a mirror image. It is not. It is not because this also is essentially trap state emission. And this has a really long lifetime. Now look at the x-axis. Well, on y-axis, we have fluorescence intensity, let us say. On x-axis, we have time. And this sharp increase that you see here, perhaps I should have said this earlier, this is where the light has gone on and off. So excited state population has been created here. Photoluminescence occurs on excited state population, and that decay sort of mirrors the decay of excited state population. So let's not get into too many time constants. Suffice to say that the time constant we get is 48.25 nanosecond. We still have a lot of fast components, and we are yet to resolve it. I mean, we have resolved it, we're not discussing today. But look at the photograph. This is how strongly it emits when excited by UV light. And that is because of this long lifetime, long-lived trap state. So trap states are not always bad. They can be put to good use. And now I draw your attention to this relative photoluminescence quantum yield. It is 62%. Remember the numbers we were talking about in nanotetrapod. From there, 0.008 and all, we have come to 62%. This is a huge improvement. especially because this is completely, well, made in water, made for water kind of thing. So there has been some work on metal ion sensing and all, but it's too premature to discuss them now. So this is a summary of nanotetrapods. The idea is not only nanotetrapods, even this cadmium cyanide and all, one can engineer trap states to control emission properties. And what I have not shown you in detail is that we think that even those bad water-soluble nanotetrapods of ours, which are not emissive, they have some potential for drug release. We are doing some experiment of interaction of a warfarin-loaded human serum albumin with this nanotetrapod, and we have got promising results, which let it be the story for another day. Do I have any more time at all?
Well, actually, no.
Okay.
It's 2 minutes. If you can wind up in 2 minutes.
Yes, I will. So, right. In any case, I don't want to talk about this because I have given, I don't know how many webinars I've delivered in the last 4 or 5 months. Almost every time I've talked about this part. One of our recent interests is in fluorogenic molecules. Because of its applications in solid-state photoemitters, we started working with shift base. And if I am to summarize in one sentence, what we have learned is that if we want good emission from solid state from this class of molecules, we must avoid pi stacking in whichever form it might be. Electronic factors are important, but mostly whether these molecules will emit in solid state or not is determined by structure. And the other molecule that we have been working on in collaboration with Professor Anil Kumar's group, it has contributions from which it was started by a postdoc Anushwa, who's now a faculty member in Odisha, continued by another postdoc Shomuditto and Shomishta. So what we saw is that if you take this model, it has a very flexible structure. So in a nice homogeneous solution, it doesn't emit because there are so many excited state processes that can be activated. But when we add a bad solvent, water, and make aggregates, it fluoresces strongly. I'll just go and show you something else. You heard about FLIM. So the good thing about FLIM is that you can do many, many different things. What Sharmishta and Shomuditya have done is that they have looked at these aggregates that we have prepared of these fluorogenic molecules with surfactants, and they have looked at how frequently you see a particular lifetime. And they have established that at small concentrations, you get aggregates that are spherical or some are small rods and all. Lifetime is about 1 nanosecond. When the rods form, you get longer lifetimes of 3 nanoseconds. So this is the power of the technique of fluorescence lifetime imaging microscope. So if you can study ultra fast in an ultra small volume, you can really see things that you cannot see elsewhere. And this is something that has, well, come out only a couple of weeks ago. And we're very happy about that this little bit of abstract artwork of Shomuditya has made it to the cover. The other work that is in communication, maybe I'll talk about it sometime later, is we did the same kind of experiment, this time with tri-block copolymer, and we have established that depending on what kind of copolymer you use, I'm stuck, even the computer doesn't want to work anymore, you can get aggregates that will or will not enter cells easily. So this is the conclusion, and let me acknowledge all my students, past and present, collaborators, postdocs, funding agencies. Thank you all for your patience, and thanks again to all the organizers for having invited me to this August gathering.
Thank you, Anindya, for an illuminating lecture. I guess there are a couple of questions here. The first question is by a student, I guess, asking for you to repeat the name of the classic text. You mentioned, I think, Rohati Mukherjee and...
Rohati Mukherjee. Photochemistry by Professor Rohati Mukherjee, K.K. Rohati Mukherjee.
Okay.
And the other one is by Turo. Maybe I'll write it in the chat box.
Yeah, you could. Thank you. You had a comment that said was a very interesting and important lecture. We have a question from a student here, Chirag Arora. In the preferential solvation work that you showed, are the two solvents which participate in solvation correlated in some way, or are they independent?
They are independent. So we took hexane and methanol, So that is what we wanted to do, is that hexane is just a sort of inert but liquid background that is there. And the really active component is methanol.
Okay.
So it is very different from the DMSO water kind of mixture, where there is significant interaction between the two kinds of liquids as well.
Perfect. We have the next question by Haradhan Kolia. Thank you, sir, for your eminent lecture. I do have a couple of questions. What is the role of selenium in the cadmium selenide nanotetrapods?
You don't get nanotetrapods if you don't have selenium. You need both. So the thing is, you need semiconductor nanotetrapods. So that is where cadmium selenide becomes useful.
The next question in the same series is both cadmium and selenium are very toxic to the environment. So the question is, do you have any results regarding regeneration studies?
Not yet. And because they're toxic, what we are thinking is, we're thinking whether we can encapsulate them completely in silica, or silica is our old flame, as I said. So the encapsulation in silica often makes things that are toxic much more benign. So that is very much on the agenda.
Okay, thank you. If there are no more, I don't see any more in the chat box. I have. Anybody have any question?
Yeah, one question.
Okay.
The student is very reluctant and shy to raise the question, but the question is very pertinent. He asked Professor Dasgupta whether a spectrofluorometer can be designed as an absorption spectrophotometer.
So the answer is yes and no. Yes, because you do have systems using diode array detectors and spectrograph, initially marketed by Ocean Optics. Now a lot of people are there, which you can use in absorption as well as fluorescence mode. See, when you do absorption spectroscopy, you want the light to go and hit the detector directly. When you do fluorescence spectroscopy, you want the detector to be at right angles, because you want to look at only the light that comes out from the sample and not the incident light. So if you can change the position, then you can do it. You can also do it in this pattern, but it takes a little more trick. And commercially, right now we do have instruments. The one that I can think of is Duetta by your Jobin Ivan. What is it called now? Horiba. Jobin Ivan Horiba, which is a single instrument for absorption and fluorescence. But of course, modules inside a day. That's all.
Any other question? Professor Ajay Misra have a question, I guess. I can see him raising his hand.
Yes. My question is relating to your cadmium selenide nanotetrapod.
Yeah.
So in this cadmium selenide nanotetrapod, you observe the band edge emission as well as the trap emission.
Mm-hmm.
Do you think that this trap emission, it is due to the amorphous nature of this nanocrystalline state? Some amorphous nature is formed, that's why that is going to be...
It is believed that these trap emissions are due to these dangling bonds, free cadmium at the surface, and a lot of other things. We do not know exactly what it is. I suspect that it can be heterogeneous as well. Crystallinity is well established in these systems, but then, well, as we know, the traps are all about breaks in crystalline array. So that way, yes.
Thank you.
Okay, I just have a couple of quick questions. Have you considered substitutions in the aminoquinolines, where you can increase conjugation or...
Yes, we have, and we have done a little bit. So my first postdoc, Shipra, she had actually worked on that. We did not try to, we tried to increase conjugation, that didn't work, but we did put in some electron donor group, acceptor group, and we tried to see what happens. Well, here we are limited by the fact that as far as synthesis is concerned, I have two left hands. I mean, I got really bad marks in organic chemistry practical also. So but good. Fortunately, we now have a postdoc who is a synthetic chemist, and since I have two left hands, due to survival, instincts, my students have developed some synthetic skills. That way, we are a little lucky.
Perfect. I look forward to that. Another one was about your foray into biophysical chemistry, where you talked about the missing water, So the structured water, which actually holds, say, a protein structure together, what happens to that when you wrap it with the polymer, as you mentioned?
Almost all the water is gone. We'll not say that it is gone 100%, but the water that is present is, less than 1% maybe. The Carl Fisher titration and all were done, even though I'm not very sure whether Carl Fisher titration works in a system like this. But what happens is that you essentially wrap the protein with a polymer that is liquid. So this wrapping actually brings about the structure which you otherwise see in aqueous systems. So as we know, what brings about structure is something that protein chemists like you have debated for ages. So is it hydrophobic effect, or is it just the interaction, or what is it? So what we see here is that even in a system where almost no water is there, you can bring about structure simply by sort of, I don't know what to call it, maybe steric effect, by wrapping it up in a sort of a blanket. Structure can be induced. In fact, what Convener's group has been able to do is that they have taken an IDP, wrapped it in protein, lost water, and they have observed helical structure in the IDP.
So is it forced to form a helix?
Exactly.
Okay. Oh, that's very interesting.
It is under duress.
Yes, exactly. Okay. Thank you so much for a wonderful talk. I guess we'll go on to the next lecture immediately. Thank you, Anindya. Professor Nikhil Guchhait is our next speaker. His BSc is from Presidency College, Masters from Calcutta University, PhD from the Indian Association for the Cultivation of Science under late Professor Mihir Chaudhary, followed by a postdoctoral stint in the United States of America and also as a JSPS fellow in Japan. He was a visiting scientist also at CNRS France and Academia Sinica in Taiwan. Since 2002, he has been active. His research interests are laser spectroscopy, photochemistry, and functional materials. He has over 240 publications. And for his awards, he is a fellow of the West Bengal Academy of Science and Technology and has also received the BC Deb Memorial Award in 2006-2007 by the Indian Science Congress. Today, he will speak to us about photo-induced charge transfer, proton transfer processes, some observations. Professor Guchhait, please.
Can you see my slide?
Yes, we can. No, this is only Omia's slide. You can start sharing your slides.
I already shared my slides.
Yes, we can see them. If you go to presentation mode kindly, we'll be able to see the whole slide.
Yeah, now it is okay?
Yes, yes.
Oh. So first of all, I would like to thank Professor Dasgupta for nice introduction. And I would like to thank the organizer for inviting me to share some of my very simple experimental research, what we are doing in our laboratory at Calcutta. So look, so far we have listened three talks on advanced fluorescence spectroscopy, and we have seen several advanced instruments by which you can tackle advanced problem, fluorescence-related problem to get nice information about the molecule. But if you see the title of my talk, the phenomena like charge transfer of protons is a very old problem. And
Professor Guchhait, I'm just interrupting you. We cannot see your whole slide. I don't know. On my screen, I cannot see the whole slide. If somebody would please confirm. Omio, can you see Professor Guchhait's whole slide or just part of it?
Can I start?
No, your full presentation cannot be seen. Maybe you would have to exit the whole screen presentation.
Okay.
All of us can see just part of it. Yes, now we can,
but this is.
Yeah, this is not in. Maybe you can go back to the presentation mode, and if not, we'll stick to this.
Okay.
just click on from beginning or some slide.
This one?
No, no, it's still part of it. I guess we'll have to go back to the other mode and you can continue from here. Okay.
Okay. So I have to stop.
You just have to fit to screen. You can go to view and fit to screen so that. Okay.
Enter screen if I put it. Can I get? Now can
yes,
I get it?
Yes, perfect. Thank you so much.
Okay, thank you. So look, so we have seen several sophisticated instruments and it's a nice problem in fluorescence spectroscopy from three speakers. But my part is, I think, very old problem. So charge transfer or proton transfer reactions are, I think, starting for more than 70 years. And the instrument what I am using is basically just conventional absorption and fluorescence spectrophotometer, what we have in every laboratory. Okay. So in my talk, so the outline is like this. Briefly, I will tell something about photo-induced charge transfer and proton transfer processes. Already we have listened some ICT problem from Anindya. And I specifically explained two problems, one with respect to proton transfer, basically excited state proton transfer, the another one was a charge transfer problem. And finally, summary. So if we look simple proton transfer or charge transfer process, I have two examples. These are the two benchmark molecules where it is possible to get excited state proton transfer for the left side. This is basically orthohydroxy methyl salicylate. So if you excite, the molecule exists in the enol form. So if you excite with electronic energy, in the excited state, the molecule after vertical excitation will emit two type of lights. So one from the locally excited state, basically from the enol form, and another red-shifted emission from the keto form. Actually, this proton will transfer from one oxygen to the another oxygen in the excited state, but not in the ground state. So this molecule will give you dual emission after excitation. And the right side, another molecule, this is called DMABN, where we have say benzene chromophore and one donor group, this is basically tertiary group, and one acceptor group, this is nitrile group. So for this molecule, this is basically a neutral molecule. So if you excite it, then in the excited state, charge transfer occurs from the donor to the excited to the acceptor side. And again, it's possible to get two emissions from this molecule, one from the locally excited state and other from the charge transfer state. So both processes you can explain using just a four-level excitation and de-excitation scheme, where if you excite from this level to this level, then you can expect the local emission from the molecule. Or if there is a transfer from, say, this state to excited, this state is keto form or the charge transfer state, then you can expect another red-shifted emission from this molecule. The differences between these two are, in one case, the red-shifted emission is basically shows solvent dependency, which is basically in the city emission, and other case you will not get that much solvent dependency because the polarity of this newly generated keto form or the charge transfer form are different. For keto form, the excited state dipole moment is not that much different from the excited enol form of the molecule. So stabilization of this keto form or extent of stabilization for the keto form almost same as the extent of stabilization of the enol form. So the emission, red-shifted emission will not depends on the polarity of the solvent. But in this case, in charge transfer case, what is happening due to the formation of a new dipolar state with high dipole moment, this state will stabilize with polar solvent. And depending on the nature of the polar solvent, you can expect basically red-shifted emission, a solvent polarity-dependent red-shifted emission. So this is the basic idea. Now, for these type of two problems, basically we need to measure the red-shifted emission only by simple simple conventional fluorescence spectrophotometer. So by looking at the fluorescence from the molecule, solvent-dependent fluorescence from the molecule, we can predict dual emission or charge transfer or say proton transfer process in the excited state of the molecule. So with this, we have for a long time, we have tried several types of molecules to see proton transfer and charge transfer reaction, a different type of molecule. And here, if you see the proton transfer, this side, in the proton transfer side, you have a 6-member intramolecular hydrogen bonded ring, which is a prerequisite for this type of excited state proton transfer process. But what we did, instead of only looking at the 6-member intramolecular hydrogen bonded ring system, we have basically designed different type of system with a 6-member intramolecular hydrogen bonded ring, 4-member hydrogen bonded ring, or 5-member intramolecular hydrogen bonded ring, if it is larger, to see how proton transfer will occur depending on the system. And for the ICD system, we have a chromophore, then we have a donor and the acceptor. Donor is for the DMA1 molecule is basically tertiary amine, and acceptor is basically cyanonitrile group. But here, what we did, we just intentionally changed the donor group, not only with tertiary amine, weak donor like secondary or primary amine, and the acceptors, so we have varieties of acceptors, strong and weaker. And in addition, we just intentionally change the distance between donor to the acceptor to see how these factor will control or affect the charge transfer process in this type of molecule. Okay. And additionally, we designed some molecule where in the same system, we put charge transfer donor acceptor side and also proton donor acceptor side to see the competition between charge transfer and proton transfer reaction after excitation of the molecule. And these are the work we have done. But today, I want to just focus very simple problem. One for proton transfer, excited state proton transfer, and another for intramolecular charge transfer problem. So now, if we go through the literature, what we have seen, there is a surge to design new molecule ions, particularly say metal ion or anion, or sometimes some neutral molecules. And this ESIPT type of molecules are also used as a probe to sense different type of, say, toxic ions or molecules. And if you look here, and when I go through all this paper, I have seen in some papers some controversial explanation on this ESIPT process, what they are observing and how they are explaining their experimental results. So if you look at this slide, see, there are good, I think, high-rated journals like RSC Advances, Sensor and Actuator B, like Organizator, where people want to use ESIPT molecule to sense, say, some metal copper ion, sometimes hydrogen molecule, sometime here I think maybe some other molecule like hydrogen or cysteine or H2S, S- like this. So and many more papers are there where people use ESITP molecule as a probe to study the selective sensing behavior of different type of toxic ions or neutral molecule. Now, just if you look in the next slide, so one very simple example, I have told ESIPT for orthohydroxy methyl salicylate. Here another molecule, well-studied molecule, is called HBT, hydroxybenzothiol. Here we have 6-member intramolecular hydrogen bonded ring. So proton can transfer in the excited state from oxygen to nitrogen atom to form a keto form. So this is a well-studied system. So using this type of molecular skeleton, a number of papers have been published where like protected OH group will deprotect by a molecule to sense the presence of some neutral molecule. This is called basically chemiosmometer. So what is happening if this OH group is protected by some group, it will not show any ESIPT reaction. But if you somehow detach this one, again the OH group will be free, and you can expect some emission or a proton transfer emission from the molecule. So now look some simple results which are basically reported so far. So if you look at this molecule, here same HBT type of chromophore is there, and this molecule is a sensor for cysteine or homocysteine type of molecules. And what is happening, the new band, after deprotect this OH group, a new emission band will appear around 521 nanometer light, and they assign this band is basically due to excited state proton transfer for this type of HBT type of molecule. And if you look the next one, here also the same skeleton, and this molecule actually sends H2S as reported as H2S sensor. Here, when you just add H2S molecule, this will break and will generate a OH group. That means you are now again HBT. So it will expected to show proton transfer band, and this have seen emission band around 462 nanometers. So in the first case, even if similar skeleton, they assign ESIPT band at 521 nanometer, but the other case, they assign the same ESIPT band for this molecule at 462 nanometer. So this makes some controversy. How the same type of skeleton will give ESIPT band in two different places. Okay, but when I search for the literature for HBT, I have seen the keto form for this HBT emit greater than 500 nanometer, and for this HBT anion, it emits less than 500 nanometer. This is the information already published long back with the group who are basically truly spectroscopists. Okay, then what we did, we very similar type of skeleton. We just make one compound. If you look this one, only on bromo substitution, this skeleton is basically HBT, and here is one substitution. This one is called basically protected HBT, and in our case, and this is unprotected HBT. Then we try to simply measure the absorption and emission spectra by conventional absorption spectrophotometer and fluorescence spectrum to see what is happening or what type of spectra we can expect for this type of molecule. Okay, so initially, if you make a solution for this protected HBT, you will get this type of solution only in presence of hydrogen. Sorry, in presence of hydrogen, we have little color, and dinitrophenyl hydrogen also have some color. But if you put it all this solution in UV light, you see in presence of hydrogen, the color is totally different, and you can distinctly see this coloring with respect to the other sample. So then we measure the simple absorption spectra for this molecule for protected HBT. So this is the absorption spectra for the protected HBT. It shows an absorption band around, say, 300 nanometer. Now, if you add hydrogen in the system, new band developed, and maybe that may be ultimately cause for getting this type of color in presence of UV light. Okay, so new band in the red side we have observed for this one, and then when we measure the fluorescence from the molecule, after excitation and the maximum, lambda maximum, we get basically an emission band for 382 nanometer light, which is basically local emission from the molecule. But if we slowly add hydrogen, this band slowly decreases, and we get a new band around 475 nanometer. And this is almost similar to the band what I just told in one paper. They observed the band at 470 nanometer, which they assigned as a photon transfer band from the molecule. Then what we do, we just measure the mass spectra for this system in presence this unprotected HBT in presence of hydrogen. So the first spectrum is like this. We have this protected HBT, then we add hydrogen and keep it for say more than overnight, and the next day we measure mass spectra for this molecule. See here the peaks are basically for the peak for the unprotected HBT. Only, yes, this is unprotected HBT. But the second spectrum is like this. We just put hydrogen and immediately we measure the mass spectrum as same. So this is the peak for the protected, and these are the peak same as this one unprotected. And here some adduct for hydrogen and protected HBT. So this can say is that the unprotected HBT was from protected HBT in presence of hydrogen, and we can say hydrogen can sense due to the formation of unprotected HBT. The question is this unprotected HBT. What we have seen in the fluorescence spectra is shows the band at 472 nanometer or something else. Okay. Then what we did, we again the measure the absorption and fluorescence spectra for the unprotected HBT. Here we have seen nice absorption spectra for the unprotected HBT, and if you put say hydrogen to the system, a new one generated around 403 nanometer, which we observe for the protected also in the absorption spectrum, and then in the emission spectra, what we have seen for this unprotected one. If you measure absorption spectra, you will get, say, emission around 520 nanometer. But if you add hydrogen, then the band is shifted to around 470 nanometer. Okay. So then we thought this 520 nanometer band is basically in absence of hydrogen, means this is the photon transfer band for this molecule, unprotected molecule, and 470 nanometer band is basically due to the formation of anion. So if you add hydrogen to this type of system, it will form an ion, and the emission band or absorption from the anion is different from the photon transfer band for the molecule. So by this way, and by comparing basically the absorption and emission spectra, we have shown that this type of HBT molecule shows ion emission in presence of say hydrogen, but not due to ESIT process. The problem is when I was seeing this type of sensing paper on ESIPT, without properly analyzing the spectral data, I have seen people are just citing it is ESIPT, or sometimes due to suppression of ESIPT or due to enhancement of ESIPT, but looking at the structure, they do not see properly what is happening in the molecule. So I want to focus here just only by looking, without looking at the proper or analyzing spectra, you can sense the molecule using ESIT probe as a probe, but you need to know, or you have to properly analyze the spectra. What Anindya told, like for some methyl cyclohexane, the polarity will non-polar molecule is transferred to polar molecule at low temperature. But that is not the true case. But this type of information you will get when you just look this type of paper. Okay, and the next. This is I want to convey from this one. Instead of just only looking the spectral change and telling something, whether it's SIPT or photon transfer or something else, without analyzing the spectra, it's not good. Okay. But our result clearly indicates that this type of molecule, when interact with some say analyte, particularly some molecule, it will form say, anion. So anion band, emission band is distinct at around 4. And neutral ketoform emission is around more than 500 nanometer. So you need proper assignment of the spectral data. Okay. The next one, just another problem I want to say. This is charge transfer problem. I already told for DMA-BN molecule. This is the neutral molecule. If you excite with this, or electronic transition, if you do, you can generate in the excited surface a charge transfer state with higher dipole moment. And this type of molecule, after excitation, will give dual emission. The red-shifted emission shows a solvent polarity dependency. The position of the band basically depends on solvent polarity dependency. This was the experimental observation. And this type of phenomena was explained by different type of theoretical model, but the most accepted one is basically TICT model. So TICT model is like this. So it is like this. So in the excited state, the charge transfer state is that one where this CN group is twisted at 90 degree configuration. So with respect to this twist coordinate, if you plot the potential energy, then in the ground state, you will have basically single minima, but for the excited state, you have two minima. So this is the locally excited state, and in the excited state, charge transfer occur. So at the 90 degree configuration, you can generate a low energy structure, which is basically the ICT state, and that will relax to the ground state with the with giving some emission, this is CT emission from the molecule. As it is CT state, so the stabilization of this state basically depends on the polarity of the solvent or dialectic constant of the solvent. So the band will shift to the red or blue side, depends on the polarity of the solvent. And what Anindya showed in is a non-polar solvent, usually we do not expect basically dual emission from the molecule, not charge transfer emission from the molecule, but in polar solvent we usually expect charge transfer emission from the molecule. And what I have seen a little more, when I search the literature, I have seen for this type of system, always donuts are basically tertiary amino group, and acceptors basically varieties like ester, acid, aldehyde, nitride. The question is, for secondary or primary amine, these are weak donor, definitely. But the question is, why these primary or secondary donor is not giving CT emission? If you look just theoretical model similar to two-state intermolecular charge transfer for like ABN case, like primary amine, if you calculate energy as a function of twist angle for the NME2 group, you'll see a single minimum for the ground state and also single minimum for the excited state. So if excited, so it will only give you the single emission and you will not expect any dual emission from the molecule. And this is actually experimental observation. And if you just switch over this NME2 instead of say para position to the meta position, then also experimentally there is no ICT emission from this molecule. So one more thing I want to say here, I have seen some very few examples where secondary amine gives some dual fluorescence. Definitely charge transfer emission is very weak, but on that system actually in the close to the amine group, there are one substitution is bulky group, which will force this NME2 group to align in the two-stage geometry. So in that case, maybe it's possible to get CT emission from this molecule. So with this idea, I choose two molecules. First of all, so I know, so far I know primary amine does not give say, CT emission, and secondary amine gives CT emission when there is a bulky group. So my molecules are very simple. Look, this is primary amine. Intentionally, I put say one methyl group so that it will force this NME2 group to twisted geometry, because this twisting is responsible for CT process in the excited state. And here I put some ester group because ester strong electron withdrawal group. So maybe it's possible to get emission from this type of molecule. And another one, here I put say NH2 primary amine in the meta position and my methyl group, bulky group in the para position. So this bulky group also try to force this NME2 group to be twisted geometry. And if you look these two molecules can form two isomer, basically conformer with respect to rotation of this CC bond, because this CO group just same side of this methyl group or the opposite side of the methyl group, right? By this way, if you just calculate the structure or global minimum energy for this structure, you can generate two structure with little difference in their energy, but transformation from one to the other need to rotation of this one, then the barrier for this one is quite high. So maybe it is possible to get these two structure in the sample, but we cannot differentiate this one by simple broad spectrum in the absorption and emission spectra. So first we study simple absorption and emission spectra for this molecule with paraamine, and then with metaamine and see whether we will get only the single emission from the molecule or dual emission from the molecule. So first try with the first one. Look. This is the simple absorption spectra for para-amino compound. This absorption peak is around, say, close to 290, 295 nanometer. It's basically for benzene chromophore. What amine substitution is there, so it is a little bit shifted with respect to benzene. But the position of the band has very little dependence on polarity of the solvent. But when you want to look the emission spectra from the molecule, we have seen the left side is basically in cyclohexane, and if you move or increase the polarity of the solvent, the emission band is shifted to the red, and then shifted around 40 nanometer. Okay, so the question is why this type of shifting occurring, even if we have say primary weak donor, and we expect only single emission from the molecule. Okay. Then what we did, simple, just conventionally, we tried to just plot it, the standard Lippard-Matlaker plot for emission band position, basically Stokes shift, at different solvent, we see a linearity. And from there, we found that the excited state dipole moment is around 7.14 with respect to a certain ground state global minimum structure, where the ground state actually dipole moment is around 3.56 dBi. So with respect to the experimental result, we have seen the dipole moment is almost double for this molecule. So that indicates that the species which emit the redshifted emission, solvent polarity dependent redshifted emission, is nothing but a charge transfer emission from the molecule. The question is charge transfer from where it will occur. So the simple, these are just the same thing. I want to see basically the position of the emission band depends on hydrogen bonding parameter of the solvent and dialectic constant of the medium. Okay. Then what we did, we just intensely put little acid H plus to see the absorption and emission of the molecule. Because we have lone pair, that lone pair will move from, say, donor to the acceptor side. So somehow if you block H plus ion, H plus, by H plus is lone pair, by generating a cation, we should not expect any charge transfer from the molecule. And that's happened from this experiment. So if you add basically H plus ion, the absorption spectra shifted to the blue side because you will generate a cation. And now there is no question of, say, charge transfer or so flow of lone pair through the ring. So definitely no stabilization is there. So you can expect a blue-sided absorption for the molecule. And if you look the emission spectra, so emission spectra, CT emission slowly decrease and you will get a local emission from the cationic state. So this will tell that this lone pair will move from the donor to the acceptor side, clearly, which will generate a dipolar state, and the stability of the dipolar state depends on the polarity of the solvent. Okay. Then we measure just usual lifetime for the molecule, standard just TC system. And what we have seen in highly polar solvent, we have single exponential decay for the CT state, but for non-polar type of solvent, we get, say, bi-exponential decay, like in cyclohexane type of solvent. And for protic solvent also, we get bi-exponential decay from this molecule. So it seems maybe in non-polar solvent, we expect basically single emission, and we have one emission, only the broadness is there. But I don't know why actually we have double exponential decay from this molecule. But later on, hopefully we can explain this one. Okay. Then for the next one, when we have basically meta-amino system, here also when we get the absorption spectra similar to the aniline type of absorption spectra, absorption band around 310 nanometer. And if you excite here, you will get solvent polarity dependent emissions here. So that means here also you can expect charge transfer emission from the molecule. In this table, you have all absorption maximum and emission maxima. The emission maximum is shifted from like 360 to say 470 nanometer. So almost 90, more than 90 nanometers shifted this band. And we plot basically, we have seen acid effect. We get the similar observation, almost similar observation. And then we plot, say, Lippard-Matlaker plot we did, and we get basically the dipole moment for the molecule for the excitation in the ground state. Ground state is basically we optimize the structure, get the ground state dipole moment, and using this one, we can get excited state dipole moment for this molecule with respect to this redshifted emission. And here also, look, the dipole moment for the excited is more than double for the emission or for the redshifted emission, or we can say for the charge transfer state. So up to this one, so for these two molecules, even if primary amine, we can say the redshifted emission or solvent polarity dependent emission, what we are getting is basically charge transfer, even if it's primary amine. And one more thing, even if not only the para position amine group is responsible for charge transfer, meta-amine also can do similar charge transfer in the excited state when you excite the molecule in the locally excited state. Okay. But I don't know why in cyclohexane we have basically for both cases here also. So if you look in cyclohexane, we have bi-exponential decay. Only in non-polar solvent, you have local emission part higher compared to the CT emission, but in polar solvent, actually CT emission is higher than the local emission. This is the only observation. Then what we did, we want to see, because we have seen this result, and we want to see whether it is possible to get some information about this twisting motion. So because as per the model, twisting is responsible for getting 90-degree charge transfer state. So somehow we can pick up the twisting motion. I think we can say something about this one. And this is only possible not by this type of broad spectrum. What I have to do, we have to somehow get high regional spectrum for them. How can I get it? Just going to the gas phase spectra. Here I have shown spectra for aniline. What I did in the lab, just excitation spectra for aniline and non-polar solvent. And if you look carefully, some undulation, there is a very slow scan. We did it. It seems some vibrational structure, a little bit low temperature, we did it. And then intentionally in the cuvette, instead of getting the spectra in solution, we put just aniline vapor, aniline 1 drop, and the vapor is generated there, and then we check the excitation for this molecule. Then simple evaluation, a fluorescence spectrometer, we get nice structure. But still, this will not allow us to say something about low frequency modes. Okay. To get low frequency mode, we have to go through, say, low temperature means in molecular, supersonic jet cooled molecular. And this is the spectrum of aniline close to the 0-0 transition. And you see highly resolved spectra with different type of modes. Clearly, you can assign all these modes. And we have picked up basically for aniline inversion motion and its progression. So, and for this type of experiment, to get basically high regional spectrum for this type of molecule, we developed a molecular beam setup in our laboratory. And the setup is like this. This is very simple setup. So this is a vacuum chamber. Here is one valve. So we have to drive it. So we have to put sample and some carrier gas at high pressure and expand it to the vacuum. By this way, you can generate low temperature molecular beam and then excite this low temperature gas phase molecular beam with some tunable UV light. And after excitation, molecule will emit some light that we can pick up with the photomolecular tube and finally process with boxcar integrator and plotter, oscilloscope or computer. So, and for synchronization of molecular beam with laser light, we have one pulse generator. So this generator will simultaneously generate 2 pulses. One will trigger the valve driver, another will trigger the NDA laser. Like if you look carefully here, 2 pulse, NDA laser, then from here dye laser, second harmonic crystal, you get UV tunable light, then it will interact, give you some fluorescence from the molecule. So ultimately you can collect the fluorescence to get nice information about the molecule. So, and using this setup, we try to measure laser-induced fluorescence, excitation spectra, and emission spectra, dispersed emission spectra for these 2 molecules and see what is happening. So the first one is basically para-amino molecule. And if you just measure laser-induced fluorescence, we have nice spectrum. And if we analyze this one, it seems the first strong 2 bands are basically 2-0-0 transition for the 2 conformer. Because this molecule can form 2 conformer, 1 and 2, with respect to rotation of this one. That means this O group is same side of the CH3 group, the other side. So these 2 bands are basically 2-0-0 band. It's not possible to get this type of information in simple condensed phase broad spectrum. So these are 2-0-0 band, and we have several low frequency band. The thing is, they are coming at spares. Spares means that means same type of frequency is coming out after 15 wave number interval. Okay, and these are low frequency mode. Hello.
Professor Guchhait, you have about a couple of minutes left.
Okay.
If you could please wind up. Thank you.
Okay, I with 2-3 minutes I can complete it. Okay, and then if you look if you calculate basically energy with this rotation and twisting motion of this one, we can have 2 conformer. Energy difference is very small, but barrier for conversion is quite high. So in the jet, both will populate in the jet. And if you excite it, you will get individual excitation spectra for conformer and conformer 2. And we try to basically match the vertical transition energy with theoretical calculated vertical transition energy. We have seen in the excitation spectra, we have only 15 nanometer difference between 2 conformer, but in calculation, we get basically 19 nanometer. So it's matched well. And then we try to basically get the dispersion spectrum. So dispersion means we excite the first conformer, the 0-0 band, and see the structure band with a broad spectrum. For 0-0 plus 15 nanometer, the second conformer, again we get structure band and then broad spectrum. Then we just intentionally excite the first quantum of some torsional motion like 00 plus 52. Then we get more, say, broad. Basically, this is CT band. And here also 00 plus 75 means basically second conformer and its first low frequency mode. That means this molecule without any solvent, like what Anindya told, in presence of a non-polar solvent, they get CT emission, charge transfer emission. Here in the isolated condition also, we have pick up, in addition to local emission structure band, some charge transfer rate CT emission in solution in the gas state, and we don't have basically need to stabilize the CT state. Okay, and next, for the second molecule, the meta component also, we have a layer in this fluorescence excitation spectrum. Here we analyze this one. We have conformer 1 and conformer 2, similarly with respect to orientation of the ester group, CO group, and there are low frequency mode a little bit different, but the modes was calculated with respect to Gopal structure. Then we correlate it and we assign all this band. Okay, these are basically the different type of modes. Okay. And for these molecule particularly, still we are try to do basically single vibrant level emission spectra. We have some result preliminarily, but due to lockdown we cannot pursue that one. But hopefully we will get for this one also in the gas phase without any solvent. We get CT emission by excitation of the 00 band, or maybe in 00 band we can get only the local emission. But if you give a little bit more energy to the system, like in the twist coordinate, maybe it is possible to get CT emission from the molecule. So overall conclusion is like this. So the first case I want to mention that anion formation, but not ESIPT, is the main cause for sensing of different type of say analyte. So before going to say something about your result, particularly for sensing case, better to analyze the spectra properly, and then you can assign all bands. And the second case, basically for para and meta amino compound for primary amine, also we can get sheet emission in condensed phase. Only thing is we have one bulky group close to the donor. Maybe that will try to twist the NH2 group to get with the twist structure. And in the gas phase also, we get CT emission for the first case. Second case, we want to do this one, while we're doing this one. And these two works, the first work was done by Dr. Orgadi Bhattacharya, and second one by Subhas Makhal. And my funding is from DST and CSL. And thank for your attention.
Thank you very much, Professor Guchhait. We have, I guess, a couple of questions. One, well, most of them are by Mukul Mahato about whether DCM is dichloromethane. That was one of the questions. And one of the questions was the effect of solvent in photoemission spectra, which I guess was the basic premise of this. So if you would just want to summarize, Professor Guchhait, the effect of solvent in photoemission spectra.
So here basically in our case, for ICT process, basically what the charge species will generate after excitation. So if we just change the nature of the solvent, particularly dielectric constant, that will stabilize the CT state more. So we can expect basically more reciprocate emission from the molecule. So in solvent case, basically that will occur. And we say like this way. But unfortunately, when we try to, because this type of gas phase spectrum, for all molecules, there is no information about the structure of the molecule in the ICT state. Because the ICT state is transient. So if you want to get some information about the transient state, after generating that one, you have to do spectroscopy to get what is the structure of that transient state. It's not possible. Possible means if somebody has some two-color experiment or multicolor experiment, they can do it. By this type of just absorption and fluorescence spectrometry, it's not possible. But what I want to say, even for our case, in gas phase, without solvent, we get basically, in solution phase, we get it. But in gas phase also, we get CT emission from the molecule. So I don't know how charge state is stabilized in the excited state without solvent with respect to the neutrals. I don't know that one. What is the cause? Maybe some theoretician can give some information about this one. But the experimental observation is, if you excite the molecular 0-0 transition, you will get local emission, structure emission. In addition, you will receive broad emission from the molecule. This is the observation. Okay.
Thank you. Professor Guchhait, we just have one last question from Ajanta Joseph. When the molecule possesses two conformers, if it emits two emission, one at a shorter wavelength of say 420 nanometer and one at a longer wavelength of 590 nanometer in non-polar solvent, and a single emission, say 420 nanometers in the polar solvent, how can it be correlated to the molecular structure?
Actually, it will only tell molecular structure. Like from broadband, it's not possible to tell something about the structure of the molecule, like fluorescence. Only you can say something. The transition is in the blue side, means you have a chromophore where you have say less stabilization or energy gap between two levels. I think more. And if it is in the red side, you can say the energy gap between two levels are less. But you cannot say anything about the structure. In broadband, you cannot do. Only you can get the information about the transition, where it will emit. That one you can get. Structural information you cannot get. If you want to get structural information, what we are doing? Usually we are doing IR spectra. Any sample when you synthesize it, first we do IR spectra, FTIR spectra, to get what type of functional people they are. Right. By broad spectrum you cannot do.
Thank you very much. Are there any questions? I just heard somebody. Anyway, so I guess we'll wind up this session. I thank both the speakers for their wonderful lectures, and over to you, Omio, for the final session.
Oh, thank you, Professor Dasgupta, and as well as the both eminent speakers, Professor Dutta and Professor Guchhait, for your timeliness and nice presentations. And without any further delay, we'll now move to the concluding remarks. We'll now go to the concluding remarks, and we'll like to get the feedback from you all. And may I request the four speakers to remain present. And I request Professor Swagata Dasgupta and Professor Ajay Misra to kindly chair the session. So first, I would like to get some feedbacks.
Well, I guess we've had a long day, starting a webinar, a very fruitful webinar, and I do hope the students have taken back a lot of information, particularly a lot of basic information, starting from what fluorescence is to even very high levels of research. I for my personal thing, it was a very, very fruitful and very well informed lectures, and I'm sure the students as well as faculty have benefited from it.
Yeah, the feedback from the participants. You can just unmute one by one, and you can just give your feedback. Professor Anunay Samanta, are you there? Professor Samanta? Professor Anunay Samanta? Professor Anunay Samanta?
I am there, very much there.
Please, your assessment, because you are the most eminent personality among all the participants and the speakers, and with due regards to all the persons.
I discussed something very basic. I really did not speak about my, perovskite research. Today, because it's advances in fluorescence spectroscopy, I thought that I will talk about some, basic advances, how we can go to single molecule level and discuss. I don't know how much people have followed it, really. That I don't know.
Professor Swagata Dasgupta.
Yes, I'm sure they have, and you are welcome for another lecture with your perovskite work later on. That would be, Yes, some other time, I'm sure.
When you and Omio say something, invite something, I can't say no. That's my problem.
Okay. So we'll keep that in mind.
Okay.
Thank you so much for accepting and being with us for this time. I understand it's quite late. And we would also want from the participants suggestions for future webinars, topics that you would like to be conducted here, and if you want specific speakers you would like to listen to, because this is a platform where you don't have to travel. You may have a late lunch, but you don't have to travel. And Professor Nilmoni Sarkar, you are the next speaker if you would like to tell us something.
Professor Nilmoni Sarkar.
Yes. I think this is a very nice initiative by the CS local chapter as well as the Vidyasagar University, because I have mentioned in my lecture also, fluorescence is a particularly tool. If you see in a particular department, as for example, I can tell you in my department we are around 34 faculties, maybe 20 or more. Faculty members are using this tool for some purpose actually. So maybe not very advanced level research, but as for example steady state spectra, many people are doing and interpreting the results. So this is a very nice initiative, and this should be continued in a local level, so that many students are exposed, and the college, the faculty members who are working in college, they can maybe not directly related to research, but they can continue to DST ACRV initiative, that is the TIAR project. They can do work with some colleagues, and that will be, I think, good thing. And another thing that we can encourage our young students to do more actually related to this, because this is a versatile technique, and most importantly, if you consider biological systems and biological processes where you can use it very efficiently, even in medical purposes also. Many of us actually don't know how one can use, particularly imaging and other techniques. Actually, one can very efficiently use, particularly for medical purpose as well as for many biological problems. That's all.
Thank you so much. Is Professor Dutta there? You could share your feedback.
Professor Anindya Dutta.
Yeah, I'm there. Just this computer is not as ultra fast as our equipment. Yeah, so it was for me. It was a privilege learning from the talks of other senior colleagues in the field. As I told Anunay, whenever I hear anything from Anunay or Niluda or Nikhil, we learn a little bit more. So it was an enriching experience. And Professor Sarkar is sort of like my second guru, because he was the senior most student in our lab when I was a PhD student. So how to handle a laser and all, I learned a lot of things from him. It's always a pleasure hearing him. It's sort of reunion of sorts. And I hope the students would have, the pace was very nice, because first two talks, all the basics were built with glimpses of research. And Nikhil and I tried to present more of our research. So I hope students would have gathered some idea. As it famously said that, 1/4 is learned from guru, 1/4 from friends, 1/4 by oneself, and 1/4 only with time. So we hope that initial 1/4 and all that is taken care of.
Thank
you. It's always a pleasure to accept invitation of senior colleagues like Ajay and Omiyada Swagata. The only thing we missed a little bit was sharing Omiyada's tiffin box, which I did last time.
Next time, once the normalcy is restored, then definitely.
Sure.
Yeah, now that's the I am in an advantageous position in that sense that yes, I am privileged. Whenever I request Anunay, Nilmoni, Nikhil, they usually don't deny, and that's the benefit for the society, for our students who otherwise don't get opportunity to listen to them.
Absolutely, I agree with you completely. And I guess we could all, it would have been wonderful had we been together. But these webinars make you even listen to lectures where you don't have the travel involved. So in a way, it is a good thing. Because I wouldn't expect either Professor Samanta or Professor Dutta to come right over to Kharagpur or to Vidyasagar University to give their illuminating lectures to us. So in that sense, this is a privilege in that sense. So I do hope in the future that we could hear more of such lectures. Professor Guchhait, we would like to hear a word from you too.
Oh, well, I want to say one thing. So when you will have any other type of topics, so you can inform us so that we can participate on that talk. At least we can listen to this talk. Because this
absolutely. Well, then it will become a selling issue that are you a CRSI member?
Anywhere in this chapter, if any talk.
Perfect.
So
absolutely.
you arrange it, you can inform us.
Sure. Okay. We will create a local group also, and then we will involve you as well. Sure.
Okay. Thank you.
No,
Professor Misra?
Feedback.
The feedback form, is it ready? We will send the feedback form from you?
We'll share the feedback form. Yeah, we'll send the feedback form, and definitely we are expecting to your valued feedback. We'll be sharing with you.
Okay. Professor Misra, would you like to give the final word?
So, yes, it was really a wonderful time to all of us to listen the recent advances in fluorescence spectroscopy from the eminent speaker for today's webinar. All the speakers presented their work as well as the fundamental aspects of fluorescence spectroscopy. And the participants asked some questions, interesting questions to the speakers, and speakers clearly clarify those questions also.
To everyone by email.
Also. Now, what are the takeaway message from this webinar? So I think the fluorescence spectroscopy is a versatile technique to be used in the molecular level as well as in the bulk level or in the material science, be it in vivo or in vitro study. And also lots of research work are still to be done in this field of pure chemistry or in the biophysical chemistry or nanochemistry by using fluorescence spectroscopy. So in a nutshell, I can say that today's webinar is successful as it is reflected from the number of participants. That is, I think, process more than 350. So with these few words, I think I thank all the speakers, participants, our university authority, and the CRSI Kharagpur local chapter to make this webinar successful. So thank you.
Omio, you can take over.
Anything else? No, so I have nothing to say. Everything has been said by Professor Ajay Misra. Actually, nothing should be said after this because he has formally given the vote of thanks.
Perfect.
So, on behalf of the organizers, I once again convey our deep sense of gratitude to the speakers and to all the participants. And please be in touch. We'll be bothering you again and again, and we'll be sending you with forthcoming events. I thank you all. So with this, with your kind permission, let us conclude. Thank you very much. See you again.
Bye.
Hello, Anunay, ভালো আছেন? অনুনয় দা,
এই অনুনয় দা, আপনাকে নিখিল কি বলছে?
অনেকদিন দেখতে পাইনি তো আপনাকে। ভালো আছেন?
ব্রজবাবু না নিখিল?
হ্যাঁ
নিখিল। অনুনয় দা আনমিউট করতে হবে।
নীলুদা কেমন আছেন?
ভালো আছি, তোমার তো খোঁজই পাওয়া যায় না।
বাড়িতে বসে আছি পুরোপুরি।
নিখিলদার খোঁজ কোনোদিনই পাওয়া যায় না।
অনিন্দের সঙ্গে দেখা হয়েছে মানে টকে
আমার কেমিক্যাল করেছে। হ্যাঁ
হ্যাঁ,
এই জন্য আমি আনমিউট করেছি, ঠিক আছে? আমি কথা বলবো সবার সঙ্গে আলাদা করে, অমিও, ঠিক আছে?
হ্যাঁ 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 হ্যাঁ, আচ্ছা 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 আচ্ছা, ঠিক আছে ঠিক আছে ঠিক আছে।
অনিন্দের সঙ্গে দেখা হয়েছিল কেমিক্যাল সোসাইটি টকে।
হ্যাঁ, কেমিক্যাল সোসাইটির টকের দিন দেখা
আমাকে সারাদিন ওখানে বসে থাকতে হয়েছিল, সকাল থেকে 8টা থেকে।
না, আজকে মোটামুটি
অনিন্দর অনেক চেঞ্জ হয়ে গেছে, মানে তোমার দেখে
ওয়েট কমেছে তো, ওই দিন বলেছিল
আমি তো প্রথমে চিনতেই পারিনি যে ছবিটা পাঠিয়েছে, আমার বলে তো অনিন্দ অনেক চেঞ্জ হয়ে গেছে। তো অনিন্দ, তোমার লেকচারটা আমার খুব সুন্দর লাগলো।
আচ্ছা, থ্যাংক ইউ।
প্রত্যেকের লেকচারই ভালো লেগেছে, তোমার লেকচারটা খুবই ভালো।
এর পরের পার্টটা যেটা দেয়নি সেটা আমাদের এখানে কেমিক্যাল সোসাইটি দিয়েছিল, তাই তো অনিন্দ?
হ্যাঁ 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 হ্যাঁ, ঠিক বলে। ওই টকটাই ওখানে দিয়েছে, ওইটাই সব জায়গায় দেওয়া হলো। তাহলে যে একই জিনিস বারবার করে বলা হচ্ছে, খালি টাইটেলটা পাল্টে যাচ্ছে, আজকে একটা অন্য কিছু বলি। সেটা একটা টক বানানো হয়ে গেলে তখন আবার আরেকটা বানানোর চাইতে সেটা বলে যাওয়ার ইনার্সিয়াটা এসে যায়। এরপরে
চলছে গো।
মেয়ে কি ক্লাস হবে নাকি? মেয়ে ক্লাস শুরু হবে নাকি?
কোথায় ক্লাস? কিছুই তো হচ্ছে না,
বন্ধ আছে, তাই তো?
হ্যাঁ।
হেড কিছু বলো
না। আমি তো এখন হেড নই, আমি ফরমার হেড। প্রাক্তন বিভাগীয় প্রধান।
আচ্ছা,
ওটা শুনতে ভালো লাগে আর কি, বিভাগীয় প্রধান বললে। অমিয় স্যার
বলো।
হ্যাঁ, বলো তুমি।
আর কি বলবো, এই তো আছি, ভালোই আছি। হ্যাঁ, আর কি বলে, আমার সে অনিন্দর কথা মনে পড়ে গেল। অনিন্দ কলকাতা এসেছে, ওকে বললাম তোমাকে মেদিনীপুর আসতে হবে। অনিন্দ কেন, এটা মনে আছে।
হ্যাঁ, ওটা খুব ভালো হয়েছিল, বেশ বাংলায় টক দিয়েছিলাম।
একদম, আজকেও বাংলায় দেওয়া যেতে পারত, কিন্তু আজকে পুরো এতে ছিল।
আজকে বাংলায় দিলে ভালো হতো না, আজকে অনেকেই বাইরে
আউটসাইড বেঙ্গল ছিল। না, অনেকেই করেছে, যাই হোক আমরা খুব শর্ট টাইমে করেছি এবং ইউ অল হ্যাভ কাইন্ডলি অ্যাকসেপ্টেড দ্য ইনভিটেশন। এটা একটা আমাদের
ফ্লোরেসেন্স স্পেকট্রোস্কোপিতে এর চাইতে ভালো স্পিকার হতো না।
আর হ্যাঁ, আমি বলছি তো ন্যাশনাল
একদম
ভালো স্পিকার পেতাম। প্রথমে অজয় একটু কিন্তু করছিল, আমি বলি ধর আমি আর অন্য নয়, এই 4 জন বলে একই স্কুল। আমি বলে হ্যাঁ, একই স্কুল থেকে হোক, কোনো অসুবিধা নেই।
আমি কিন্তু করেছি, আমি নাম দিয়েছি।
আমরা প্রথমে শুধু স্পেকট্রোস্কোপি বলেছিলাম, তারপরে অজয় বললো না, এটা তাহলে ফ্লোরেসেন্স স্পেকট্রাই করে দাও। বললো হ্যাঁ ঠিক আছে, ফ্লোরেসেন্স স্পেকট্রোস্কোপি। কিন্তু নিখিলের ছবি পেতে আমার খুব যেতে হয়েছে। হ্যালো, নিখিলের ছবি পাইনি আমি।
ছবি পাঠালাম।
হ্যাঁ, ওইটাই তো
তুলে পাঠিয়ে দেবো,
ওটাই তো দেখালাম।
এরকম ছোট ছোট 3-4টা টপ হলে বসে শোনা যায়, সারাদিন সকাল থেকে বিকেল পর্যন্ত হলে চলে যাবে, বুঝতে পেরেছো? এই 4টা টপ হলে সন্ধ্যে সব শুনলে মোটামুটি ঘন্টা 2
4টে টক 45 মিনিট করে হয়, কিন্তু এত অনেক বেশি হলে তখন আর গুলিয়ে যায়, সম্ভব হয় না বসে।
হ্যাঁ, তখন আর ধৈর্যও থাকে না, আর বাড়িতে বসে করলে থাকবে না কেন, এটা ওটাতে ইনভলভ হয়ে যায়।
আরে এ তো টক, আমরা পিএইচডি অ্যাডমিশন ইন্টারভিউ করলাম, নীলুদা তোমরা করেছো নিশ্চয়ই। পিএইচডি অ্যাডমিশন ইন্টারভিউ টানা 10 দিন 12 দিন, সকাল থেকে সন্ধ্যে পর্যন্ত একটা হলো।
হয়নি তোমাদের মতো।
তুমিও ভালোই হলো, ঠিক আছে, ভালোই হলো। হ্যাঁ,
কিন্তু আপনাকে মিস করলাম মেদিনীপুরে, যেটা আপনি মেদিনীপুরে থাকেন। হ্যাঁ, সেই
আমার মার্চ মাসের 26 একটা লেকচার ছিল মিদনাপুর কলেজে।
হ্যাঁ,
সমস্ত কিছু কনফার্ম, টিকিট ক্যান্সেল করতে হয়েছে, তখনই হলো।
জানি ওটা একদম ক্যান্সেল হয়ে গেছে। ওখানে আরো একজনের আরো কারো আসার কথা ছিল, আপনি তো আসতেন, আমি জানি। হ্যাঁ,
আমি 15 আইসারে গেলাম কলকাতায়, 15 আইসার কলকাতায় গেলাম, সেখানে বউকে নিয়ে গেলাম, ভাবলাম যে আবার যখন পরের বারে যাবো তখন নিয়ে আসবো। হ্যাঁ, এই প্ল্যান করে যাওয়া, দ্বিতীয়বারে গিয়ে নিয়ে আসবো। পুরো ওই মোদির ওই লেকচার হলো, একটা জনতা কারফিউ হলো, তারপরের দিনে বললাম যে টিকিট কেটে বললাম কাল তুমি আর চলে আসছো করে গেলাম। কি করবো? হ্যাঁ, সেই থেকে তুমি খুব রোগা হয়ে গেছো।
হ্যাঁ
অনিন্দ, তুমি খুব রোগা হয়ে গেছো।
হ্যাঁ, রোগা হয়ে গেছে, তা বলেছেন, ঠিকই বলেছেন।
আমাকে কে জানি এখন চোখে দেখে বিশ্বাস হলো।
সত্যি 32 কিলো ওজন কমে ফেলেছে।
হ্যাঁ, নীলমণি তো ঠিকই রয়েছে আর কি।
নীলমণি কনস্ট্যান্ট, টাইম ইন্ডিপেন্ডেন্ট ফাংশন।
অনিন্দ, এত ফ্যাট কমে যাওয়া কিন্তু বডির ভালো নয়।
না মানে ধীরে ধীরে
অজয় কোথায় গেল? অজয় চলে গেছে?
না, আছি, অনুরোধ আছি।
আচ্ছা, তোমার সঙ্গে কথাবার্তা হয়নি, ভালোই হলো। যাক, একটু টেকনিক্যাল ইস্যু থাকে।
হ্যাঁ, আপনি সুন্দর ম্যানেজ করেছেন আর কি। প্রথমটা একটু সমস্যা হচ্ছিল।
হ্যাঁ, আমি ব্রাউজার চেঞ্জ করে তখন আমি করলাম, দেখলাম যে আমহাও, আর এই তো দিন রাতি করছিস তুই তখন এইভাবে।
একদম।
হ্যাঁ,
সেটাই আমাদের এন্ড থেকে যখন কিছু বলা হচ্ছে, এমন হচ্ছে আপনাকে জ্ঞান দেওয়া হয়ে যাচ্ছে, আপনি তো এগুলো বারবারই করছেন।
না,
এটা করুন।
হ্যাঁ, যাক, নীলমণির ওই সমস্যাটা হচ্ছিল প্রথম দিকে, ওরটা কি করে
চেঞ্জ করলাম, তারপরে তো ঠিকঠাক ছিল আর কি।
হ্যাঁ, দেখে আমার দেখি শিখলে তুমি, আমি বললাম ব্রাউজার চেঞ্জ করে করলাম। যাক,
অনুরাধা ক্লাস চলছে?
ক্লাস একটু বলে আমার তো নেই, মানে আমার প্র্যাকটিক্যাল ক্লাস ছিল, এবার সেটা তো পরের সেমিস্টারে চলে গেছে, আমি বেঁচে গেছি। আমার ওই ডিন শিপের জন্য প্রচুর কাজ, এটা সেটা, এই লকডাউন, এই মানে সেই ছাত্র ঢোকানো, নানা রকম সব আছে, বাজে কাজ। 4 মাস আছি আমি সার্ভিসে, তারপর শেষ, ঠিক আছে।
তারপরে 4 মাস মানে রিটায়ার কি আর
জানুয়ারি মাসে রিটায়ার করছি, জানুয়ারি মাসে
রিটায়ার করবেন?
হ্যাঁ, 65।
তারপরে তো আবার থাকবেন, জেসি বোস পেলে আছে তো?
না, জেসি বোস তো আছে, এখানে হয়তো রিএমপ্লয়মেন্টও হবে। হ্যাঁ,
হয়ে গেল।
হ্যাঁ, 65 হয়ে গেছে গো।
এখনো একটা চুল পাকলো না।
চুল পাকলো না, এটা কিছু করা যাবে না। আমার ছাত্র আজকে বলেছে যে তো বোঝা যাচ্ছে না চুল এখনো পাকলো না, গোপটা পেকেছে।
আপনি ওই চুলে দোলের রং লাগাতে পারেন, আস্তে আস্তে রূপোলি রং।
হ্যাঁ,
চুলে ওই দোলের সময় রূপোলি রং মাখে না, সেটা লাগাতে পারেন।
হ্যাঁ, আমাকে আমার মেয়ে বলেছিল, তোমার মনে আছে 60th বার্থডের সময় আমার মেয়ে বলেছিল যে একটু সাদা রং টং লাগিয়ে যেতে। বিশ্বাস করবে না, তো সেই হলো আর কি। যাক, ভালোই হলো, গুড। এটাকে আবার ইউটিউবে দেখো না, ঠিক আছে অমিও?
হ্যাঁ,
আপলোড করো না।
না, আমি রাখছি না। আমি ইনফ্যাক্ট আমি এতে গুগল মিটেও আমি রেকর্ড করে নিয়ে আসছি, গুগল মিটেও আমি রেকর্ড করে।
এইটি ভালোই, লাইভ হলো, তারপরে দেখা যাবে। অনিন্দ্র, তোমার সঙ্গে পরে কথা বলবো, তোমাকে ওইটা করে পাঠাবো, তোমার মেয়েকে দেখেছি।
আচ্ছা অনুরাধা,
হ্যাঁ,
ঠিক আছে,
লেট আস গো ব্যাক টু,
এবার যাওয়া যাক। বাই, দেখা হবে।
ওকে, বাই, থ্যাংক ইউ।
ওকে, বাই।